The universe is 13.8 billion years old. We know that number to within a fraction of a percent. It's measured, refined, and settled, one of the most precise facts in all of science, and it has never, not once, told us when anything began. That number marks an expansion, not a start, not an ignition, not the moment existence switched on like a light in an empty room. It measures how long the cosmos has been spreading outward from an unimaginably hot, dense state. But what that state came from, what it emerged out of, or whether there was ever a first moment at all, that is a question our equations refuse to answer. Because when you run the clock backward far enough, when you compress all of space and time down toward that initial instant, the math doesn't give you an origin. It gives you a white wall, a singularity, a place where physics stops working and every model we trust collapses into noise. And so for decades, scientists have been building alternatives, theories where the universe bounces instead of beginning, where inflation never stops, spinning off infinite pocket realities in every direction, forever, where time itself curves backward like longitude at the South Pole, so smoothly that there is no edge, no boundary, no first tick of the clock. Roger Penrose has proposed endless cycles, one universe, distant future, becoming the next one's Big Bang. Stephen Hawking erased the starting line entirely, and a theorem everyone quotes as proof of a beginning actually proves something far stranger. This is not a video about the Big Bang. This is a video about what happens when you follow the evidence past the moment our certainty runs out, about the models, the math, and the physicists who looked at 13.8 billion years and realized it was never the answer we thought it was. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. We have a number. 13. 8 billion years. That's how old the universe is. Not approximately. Not give or take a few billion. 13. 8 billion years. Refined to within tens of millions of years either way. NASA will tell you 13. 77 billion years, plus or minus 0. 59 billion. The Planck satellite, which spent years mapping the faint afterglow of the early universe, puts it at 13. 8 billion. Different teams, different methods, same answer. The precision is ridiculous. We're talking about dating the entire cosmos to within a margin of error smaller than the amount of time it took for complex life to evolve on Earth. That kind of confidence usually means we've figured something out. And we have, sort of. Here's the problem. When most people hear that number, they think it means the universe is 13. 8 billion years old, the way a tree is 400 years old. They think we've carbon-dated reality itself and found its birth certificate. They imagine some kind of cosmic clock that started ticking at 0, and we've simply counted forward to now. That's not what the number means. Not even close. The 13. 8 billion years is not measuring the age of everything that exists. It's measuring how long our observable universe has been expanding. That distinction matters more than almost anything else in cosmology, and it's the distinction almost no one outside the field actually understands. Let's start with what we actually know, because the evidence for that 13. 8 billion year figure is as solid as evidence gets in science. In the 1920s, an astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, pointed a telescope at galaxies beyond our own and noticed something strange. They were moving, not drifting, moving away, fast, and the further away a galaxy was, the faster it was receding. He measured this using redshift, the stretching of light as an object moves away from you. You've heard this effect with sound. When an ambulance races past, its siren drops in pitch as it moves away. The sound waves get stretched. Light does the same thing. If a galaxy is moving away from us, its light gets stretched toward the red end of the spectrum. Hubble found that nearly every galaxy he could see was red-shifted, and the more distant the galaxy, the greater the redshift. There was only one reasonable explanation. Space itself was expanding, not the galaxies flying apart through static space like shrapnel from an explosion. The space between the galaxies was stretching, carrying them along for the ride. Imagine dots on the surface of a balloon. Inflate the balloon and the dots move apart. None of them are actually traveling across the rubber. The rubber itself is expanding and the dots go along with it. That's what's happening to the universe. The fabric of space is stretching, and everything in it is getting further apart as a result. If space is expanding now, that means it was smaller in the past. Wind the clock backward far enough, and everything we can see, every galaxy, every star, every atom, was packed into a smaller and smaller volume. Keep going, and you reach a point where the universe was unimaginably dense and unimaginably hot. That's what we call the Big Bang. Not an explosion, not a detonation that happened at some location in space. An expansion of space itself from an extraordinarily compressed state. NASA will tell you plainly, some 13.8 billion years ago, the universe was a dense, tremendously hot, extremely tiny point that rapidly surged outward in all directions. Not into pre-existing space. There was no pre-existing space. Space itself was what was expanding. This is where almost everyone gets it wrong. The Big Bang is not a thing that happened somewhere. It happened everywhere. Every point in space today was once part of that hot, dense state. You are sitting right now in a region of the universe that was once hotter than the core of the sun, denser than a neutron star, and smaller than the period at the end of this sentence. And so is every other point you can see or reach or imagine. The Big Bang didn't happen out there. It happened here. It happened at the exact spot where you're sitting. It happened at every location in the observable universe simultaneously, because all of those locations were once the same location. The evidence for this model is everywhere, literally. In 1965, two physicists named Arno Penzias and Robert Wilson were testing a radio antenna in New Jersey and kept picking up a faint hiss they couldn't explain. No matter where they pointed the antenna, the noise was there. Same intensity, same frequency, coming from every direction at once. They thought it was bird droppings on the equipment. It wasn't. What they had found was the cosmic microwave background, the CMB, the faint leftover glow from when the universe was about 380,000 years old. Before that moment, the universe was so hot that atoms couldn't hold together. Electrons were constantly being stripped away by high-energy photons, and the whole cosmos was an opaque fog of charged particles. Light couldn't travel more than a short distance before scattering off something. Then the universe expanded and cooled enough for electrons to settle into stable orbits around atomic nuclei. Suddenly, the fog cleared. Light could travel freely. The universe became transparent. And the light from that moment, stretched by 13.8 billion years of expansion, is still washing over us today. That's the CMB, a detailed all-sky map of the early universe, a snapshot taken 380,000 years after the expansion began. NASA has used it to reconstruct the conditions of the early cosmos with absurd precision. The temperature fluctuations in the CMB, tiny variations of a few millionths of a degree, tell us where matter was slightly more dense, where the seeds of galaxies would eventually form, and how fast the universe was expanding at that time. Those measurements are what give us the 13.8 billion year figure. They're consistent with galaxy redshifts. They're consistent with the ages of the oldest stars we can find. They're consistent with the abundances of hydrogen, helium, and lithium left over from the first few minutes after the expansion began. Every independent line of evidence points to the same number, but here's what that number does not tell you. It does not tell you the universe is 13.8 billion years old in the sense that nothing existed before that. It tells you that our observable universe has been expanding for 13.8 billion years. That's not the same thing. The observable universe is everything we can see, everything light has had time to reach us from since the expansion began. And because the universe has been expanding the entire time that light has been traveling, the edge of the observable universe is now much farther away than 13.8 billion light years. Space stretched while the light was in transit. The most distant objects we can detect, the ones whose light has been traveling toward us for nearly the entire history of the cosmos, are now about 46 billion light years away. The observable universe is roughly 93 billion light years across. Not because anything traveled faster than light, because space itself expanded while the light was moving through it. That means when we talk about the age of the universe, we're really talking about the age of the observable patch of space we can study. We have no idea how much more universe there is beyond that horizon. None. It could be a little bit more. It could be infinite. It could be something stranger than either of those options. We don't know because we can't see it. The speed of light sets a hard limit on how far back in time and how far out in space we can observe. Anything beyond that limit is, by definition, invisible to us. Not because it's faint or hidden, because its light hasn't had time to reach us yet. And if the expansion continues accelerating the way it has been for the past few billion years, that light will never reach us. The observable universe is a bubble, and we're stuck inside it. Now here's the part that should bother you. We have never observed the actual beginning, not even close. The earliest thing we can see is the CMB, and that's from 380,000 years after the expansion started. Before that, the universe was opaque. We can't see through it. We can model what happened. We can run the physics backward and make predictions about what the conditions were like in the first fraction of a second. And those predictions match the observations we do have, which gives us confidence they're roughly correct. But we have never directly detected anything from the so-called first instant. We can't. The light from that era, if it even makes sense to talk about light at that point, never made it out. It's sealed behind a wall of fog we cannot penetrate. So when physicists talk about the Big Bang, they're not talking about something they watched happen. They're talking about a model, an extremely successful model that explains a huge amount of data, but a model nonetheless. And here's where the model starts to wobble. If you keep running the equations backward, you eventually reach a point where the density and temperature become infinite. A singularity, a place where the math breaks down completely. General relativity, Einstein's theory of gravity, predicts that if you compress enough mass into a small enough space, you get a black hole. A region where space-time curves so sharply that not even light can escape. Run the universe backward and you get something like that, except instead of a black hole sitting inside space, you get all of space collapsing into a single point. Physics, as we understand it, stops working there. The equations spit out infinities. Infinities are not answers, they're signs that you've pushed the model past its limits. That singularity is what most people think of when they imagine the Big Bang. A point of infinite density and infinite temperature from which everything exploded outward. But no physicist actually believes the singularity is real. It's a placeholder, a red flag in the math that says something else is happening here and we don't know what it is. The singularity is not the beginning of the universe. It's the beginning of our ignorance. It's the point where general relativity, which describes gravity beautifully on large scales, collides with quantum mechanics, which describes the behavior of particles on tiny scales, and the two theories refuse to speak to each other. We don't have a working theory of quantum gravity. We don't know what happens when you try to describe spacetime at the smallest possible scales. And until we do, we can't say anything meaningful about what the universe was like at the so-called moment of creation. So here's what we're left with. The universe, or at least the part of it we can see, has been expanding for 13.8 billion years. That expansion was faster and hotter in the past. If you go back far enough, the conditions become so extreme that our current physics can't describe them. And before that, we don't know. We have guesses, we have models. Some of them are elegant, some of them are bizarre. But we don't have observations, and we don't have a tested theory that works in that regime. The 13.8 billion year age is not the age of reality. It's the age of the current expansion phase of the part of the universe we can observe. That's a very different claim. And that difference opens a door. If the 13.8 billion years is just measuring the duration of this expansion, then it's perfectly reasonable to ask what came before it. Was there a before? Did something else exist in a different state? Did the universe cycle through earlier phases we can't see? Is our Big Bang one event in a much larger, possibly eternal process? These aren't fringe questions. They're being asked by serious physicists using serious math. And some of the answers they're coming up with are stranger than anything science fiction has imagined. The singularity is where the story is supposed to start. It's the place where time itself is supposed to begin, where asking what came before is supposed to be meaningless. But the singularity is also where our equations fail. And when your equations fail, you don't get to claim you've found the answer. You've found the edge of the map, and beyond that edge, there might be something, or there might be nothing, or there might be a kind of something that doesn't fit into the categories we've been using. That's what the rest of this is about, not the 13.8 billion years we think we understand, the part that comes before it. The part where the rules break down and the universe stops cooperating with our expectations. Because if there's one thing the last century of physics has taught us, it's that the universe doesn't care what we expect. It doesn't care what makes sense to us or what fits neatly into our models. It just is. And our job is to look at it clearly, measure it carefully, and try not to confuse the limits of our knowledge with the limits of reality. The 13.8 billion year age is one of the most precise measurements in all of science. It's also one of the most misunderstood. It's not the age of everything. It's the length of time since the observable universe started expanding in its current form. What happened before that, if before even makes sense, is still an open question. And that question leads directly to the place where physics breaks, the singularity. The singularity is not a place. That's the first thing you need to understand, and it's the hardest part to wrap your head around. When physicists talk about the Big Bang singularity, they're not describing a tiny dot floating in empty space that suddenly exploded. They're describing a state where all of space, all of time, all of matter, and all of energy are compressed into a condition so extreme that the word place stops having meaning. The singularity is what you get when you take the equations of general relativity, Einstein's theory of gravity, and run them backward in time as far as they'll go. And what they tell you is that if the universe has been expanding, and if general relativity is correct, then at some point in the past, everything was squeezed into a region of literally zero volume, with literally infinite density and infinite temperature. That's the singularity. A point where the math explodes. Infinite density means you've divided a finite amount of mass by zero space. Infinite temperature means the energy per particle has no upper limit. Infinite curvature means space-time itself has been bent into a shape that makes no geometric sense. These are not real physical quantities, they're red flags. They're the universe's way of telling you that your model has been pushed past the breaking point. And yet for decades, the singularity has sat at the center of the standard Big Bang model, like a piece of furniture no one wants to move. Not because physicists think it's real, but because they don't have a better answer yet. Here's how we got here. General Relativity, published by Einstein in 1915, describes gravity not as a force, but as the curvature of space-time. Mass and energy warp the fabric of space and time, and objects moving through that warped space follow curved paths. The more mass you pack into a region, the more extreme the curvature becomes. A planet like Earth curves space-time gently. A neutron star, where a sun's worth of mass is compressed into a sphere the size of a city, curves it sharply. A black hole curves it so severely that a boundary forms, the event horizon, beyond which nothing can escape, not even light. Inside that boundary, general relativity predicts that all the infalling matter gets crushed into a singularity, a point of infinite density at the center. The math says it has to happen. There's no force in classical physics strong enough to stop the collapse once it starts. Now take that logic and reverse it. If the universe is expanding now, it was smaller in the past. Rewind far enough, and you reach a moment when all the matter and energy we can observe today was packed into a volume smaller than a galaxy, then smaller than a star, then smaller than an atom. Keep going, and general relativity says you eventually hit a singularity. Not at the center of a black hole this time, but at the beginning of everything. The entire universe crushed into a point of infinite density. That's the Big Bang singularity. It's what the equations predict. And the equations have been spectacularly successful at explaining everything that happened after that first moment. They describe the expansion, the cooling, the formation of particles, atoms, stars, galaxies. The math works beautifully once you're a tiny fraction of a second past the singularity. But at the singularity itself, the math doesn't just stop working, it breaks completely. The problem is that general relativity is a classical theory. It treats space-time as a smooth, continuous fabric. It doesn't account for the fact that at extremely small scales, the quantum nature of reality takes over. Quantum mechanics tells us that nothing in the universe is truly smooth or continuous. At the smallest scales, everything fluctuates. Particles pop in and out of existence. Energy levels are quantized. Space and time themselves, if quantum mechanics applies to them the way it applies to everything else, should be grainy and uncertain at distances smaller than something called the Planck length, about 10 to the minus 35 meters. That's a decimal point followed by 34 zeros and then a 1, unimaginably small. At that scale, space-time is expected to behave less like a smooth sheet and more like a roiling foam of quantum fluctuations. General relativity doesn't know what to do with that. It was never designed to. Einstein built his theory to describe gravity on large scales, planets, stars, galaxies, the universe itself, and it works flawlessly in that domain. But shrink the stage down to quantum scales, and the theory has no framework for handling the uncertainty, the discreteness, the quantum weirdness that dominates the subatomic world. Meanwhile, quantum mechanics, which describes particles and forces with astonishing precision, treats spacetime as a fixed background. It doesn't account for the fact that mass and energy curve spacetime. The two theories, general relativity and quantum mechanics, are both extraordinarily successful in their respective domains, but they speak different languages, and when you try to apply both of them simultaneously, which is exactly what you have to do at the Singularity, they give you nonsense. This is not a small technical difficulty. This is the central unsolved problem in all of theoretical physics. We do not have a working theory of quantum gravity. We don't know how to describe what happens when you try to compress enormous amounts of energy into a region the size of the Planck length. General relativity says the curvature becomes infinite. Quantum mechanics says you can't even define a precise location at that scale. The two frameworks are fundamentally incompatible, and the Singularity sits exactly at the place where that incompatibility becomes unavoidable. It's not a real object. It's a signpost that says, your map ends here. Roger Penrose, the British mathematical physicist who shared the 2020 Nobel Prize for his work on black holes, spent much of his career thinking about singularities. In the 1960s, he proved a series of theorems showing that under very general conditions, if you have a collapsing star and general relativity is correct, a singularity must form. You can't avoid it. The collapse is inevitable once the star crosses a certain threshold. Penrose's work was elegant and disturbing. It meant singularities weren't just exotic possibilities that might show up in specially contrived situations. They were generic features of the theory. If you take general relativity seriously, singularities are unavoidable. But Penrose also proposed something called the cosmic censorship hypothesis. The idea is simple and unsettling. Singularities, he argued, should always be hidden. Whenever a singularity forms in a gravitational collapse, it should be cloaked behind an event horizon, the boundary of a black hole. The singularity itself would be invisible to the outside universe. Nothing that happens at the singularity could ever send a signal outward because nothing can escape from inside an event horizon. Penrose famously said, "Singularities should never be naked." The hypothesis is that nature abhors a naked singularity, a singularity visible to external observers, because such an object would be a place where the laws of physics visibly break down. And if the laws break down in a way that affects the rest of the universe, then all bets are off. You lose predictability, you lose causality, you lose the ability to do science. Cosmic censorship is not a proven theorem. It's a conjecture, a well-motivated, widely discussed, deeply influential conjecture, but still a guess. Physicists have searched for counterexamples, situations where you could, in principle, create a naked singularity, and they've found a few in highly idealized mathematical models. But those examples tend to require such finely tuned conditions that most researchers treat them as mathematical curiosities rather than serious threats to the hypothesis. The general consensus is that cosmic censorship probably holds in realistic scenarios. Singularities probably do stay hidden inside black holes where they can't mess with the rest of spacetime. Except there's one singularity that doesn't fit that rule. The Big Bang singularity. It's not hidden behind an event horizon. It's not tucked away inside a black hole. It's in the past light cone of everything. Every point in the observable universe traces its history back to that singular state. If cosmic censorship says singularities must be hidden, the Big Bang is the glaring exception. And physicists are acutely aware of this. Some papers explicitly note that the Big Bang singularity has to be treated differently from the singularities that form in collapsing stars. It's not a naked singularity in the usual sense, because it's not sitting out in space where observers can point telescopes at it. It's a boundary condition, the starting point of the entire space-time we inhabit. But it's still a place where the equations break, and unlike black hole singularities, we can't just wall it off and ignore it. It's woven into the fabric of cosmic history. So what does it mean for physics to break down? Let's be concrete. Imagine you're trying to describe the state of the universe at progressively earlier times. At 1 second after the Big Bang, the temperature was about 10 billion degrees. Hot, but manageable. Particle physics works fine there. The universe was filled with a soup of quarks, electrons, neutrinos, and photons, all colliding and interacting in ways we can model with the standard model of particle physics. Go back further. At 1 millisecond after the Big Bang, quarks hadn't yet combined into protons and neutrons. Fine, we have equations for that. At 1 microsecond, even earlier, we can still describe what's happening using known physics. The temperatures are extreme, the densities are enormous, but the math holds. Now go back to 10 to the minus 43 seconds after the Big Bang. That's the Planck time, the smallest unit of time that has any meaning in physics as we currently understand it. At that moment, the observable universe, all of the space we can see today, was compressed into a region smaller than 10 to the minus 35 meters, the Planck length. The energy density was 10 to the 93rd grams per cubic centimeter. The temperature was 10 to the 32 degrees. These numbers are so extreme they stop meaning anything. At that scale, quantum fluctuations in space-time itself would have been as large as the entire region you're trying to describe. The smooth space-time that general relativity depends on dissolves into quantum foam. You can't define a precise location. You can't define a precise time. The concepts of space and time, as we understand them, cease to apply. And that's not even the singularity yet. That's just the edge of where our current theories work. Push further back, closer to time equals zero, and the density and temperature both head toward infinity. The curvature of space-time becomes infinite, and infinity is not a number you can work with. It's a placeholder that means your equation has encountered a situation it wasn't built to handle. When your computer tries to divide by zero, it doesn't give you a useful answer. It gives you an error. That's what the singularity is, a mathematical error message from the universe. No serious physicist believes the singularity is real. Not in the sense that there was ever an actual moment when the density was infinite and the universe occupied zero volume. That's almost certainly not what happened. But we don't know what did happen because we don't have the tools to describe it. General relativity, pushed to its limit, predicts a singularity. Quantum mechanics says the situation is more complicated than that. But we don't have a theory that combines the two in a way that works at those scales. String theory tries, loop quantum gravity tries, other approaches try. None of them have produced testable predictions that let us confirm which, if any, is correct. We're stuck with models that work beautifully almost all the way back to the beginning and then hit a wall. The singularity is that wall. It's a conceptual white spot on the map of physics. A region where the equations we trust, the frameworks that have explained everything else, simply stop giving answers. And because we can't see past it with our current theories, we can't say anything definitive about what came before it, or whether before even makes sense as a concept. Time itself, as described by general relativity, begins at the singularity. Asking what happened before time started is, in the classical picture, like asking what's north of the North Pole. The question doesn't pass. There is no north of the North Pole. There's no direction left to go. Similarly, if time itself emerges from the singularity, there's no earlier moment to point to. But that answer has never satisfied anyone. It's technically correct within the framework of general relativity, but it feels like a cop-out. It feels like the theory is shrugging its shoulders and saying, "I don't know, stop asking." And physicists don't stop asking. The whole point of science is to push past the boundaries of what we understand. The singularity isn't the end of the conversation, it's the beginning of a much deeper one. Because if our equations break at the singularity, that's not the universe's problem. That's our problem. It means we need better equations. We need a framework that doesn't blow up when we ask it to describe the origin of everything. This is why quantum gravity matters so much. Not because it's an abstract curiosity, but because it's the missing piece that might finally let us talk sensibly about what the early universe was actually like. If space-time is quantized, if it has a discrete structure at the smallest scales, then maybe there never was a singularity. Maybe the universe reached some minimum size, some minimum density, and then bounced or transitioned into an expansion. Maybe the Big Bang wasn't a beginning at all, but a transition point between an earlier phase and the phase we're in now. These ideas aren't idle speculation. They're being worked out in detail by researchers all over the world, and some of them lead to predictions, observational signatures we might be able to detect in the cosmic microwave background or in the distribution of galaxies. The singularity might be the end of classical physics, but it's the starting line for quantum cosmology. There's another angle to this that makes the singularity even stranger. The same mathematical structure that predicts the Big Bang singularity also predicts the singularities at the centers of black holes. It's the same physics. Compress enough mass into a small enough region, and general relativity says you get a singularity. In a black hole, the singularity is hidden behind an event horizon, safely out of view. At the Big Bang, the singularity is in the past of everything. But mathematically, they're cousins, and that leads to some deeply weird ideas. If the interior of a black hole contains a singularity, and our universe started from a singularity, is there a connection? Could black holes give birth to new universes on the other side of their event horizons? Could our universe itself be the interior of a black hole in some larger space-time? These questions sound like science fiction, but they've been explored seriously in the physics literature. The math allows for it. We don't know if nature takes advantage of the possibility. What we do know is that the singularity is not the answer. It's the question. It's the place where our best theories admit they don't know what's going on, and that admission is important. Science doesn't progress by pretending we understand things we don't. It progresses by identifying the limits of our knowledge and then working to push those limits outward. The singularity marks the boundary of what general relativity and classical cosmology can tell us. Beyond that boundary, we need something new, a quantum theory of gravity, a better understanding of how space-time behaves at the smallest scales, a framework that doesn't predict infinities when you ask it about the origin of the universe. Until we have that framework, the singularity remains a placeholder, a symbol of our ignorance, a sign that the story we've been telling about the Big Bang is incomplete. The 13.8 billion-year expansion is real. The evidence for it is overwhelming. But the singularity at the start of that expansion is not a confirmed physical object. It's a feature of the model, not a feature of reality. And recognizing that distinction is what opens the door to all the ideas that come next. Ideas that don't treat the Big Bang as the beginning of everything, but as a transition, a boundary, a moment in a much larger process that might not have a beginning at all. Because here's the uncomfortable truth. The singularity doesn't just mark the edge of physics. It marks the edge of the idea that the universe had a definite starting point. If the singularity isn't real, If it's just an artifact of pushing classical equations too far, then the whole notion that time started 13.8 billion years ago is up for grabs. Maybe time didn't start. Maybe it never does. Maybe the universe has been here in some form forever. Or maybe it cycles, or maybe it branches, or maybe it's embedded in something larger that doesn't have a beginning or an end in the way we usually think about those words. The singularity doesn't answer any of those questions, but by breaking so spectacularly, it forces us to ask them. And that's where things get interesting. Because once you accept that the singularity is a sign of missing physics rather than a description of reality, you're free to imagine what might have come before, what might have caused the expansion, what the universe might actually be beyond the 13.8 billion year bubble we can see. And some of those ideas lead to a cosmos that never stops. A universe that doesn't have a beginning at all, but generates endless regions of space and time, each one looking like a big bang from the inside. That's eternal inflation, and it's what comes next. The singularity is where classical physics gives up. It's the place where the equations admit they can't describe what happens next. But that doesn't mean the story ends there. If the Big Bang singularity is just a mathematical artifact, a red flag waving in the place where general relativity breaks down, then maybe the universe didn't start with a bang at all. Maybe it started with something else. Something that doesn't involve infinities or breakdowns or moments where the laws of nature stop working. And maybe, just maybe, that something is still running, not just here, everywhere, eternally, generating new universes the way a factory churns out products, endlessly, without stopping. That's the idea behind eternal inflation, and if it's correct, then the 13.8 billion year age of our universe is not the age of everything, it's just the age of our local bubble, one region in an infinite cosmic process that has no beginning and no end. To understand eternal inflation, you have to start with regular inflation, not the kind that makes your grocery bill go up, the cosmic kind. The idea that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion so rapid that it grew from smaller than an atom to larger than a galaxy in less time than it takes light to cross a proton. That sounds absurd. It is absurd. And it also appears to be exactly what happened. Inflation was proposed in 1981 by a physicist named Alan Guth, then at MIT. Guth wasn't trying to invent a wild new cosmology. He was trying to solve a problem. Actually, two problems. The first was called the horizon problem. When astronomers look at the cosmic microwave background, the faint glow left over from 380,000 years after the Big Bang, they see a sky that looks almost perfectly uniform. No matter which direction you point your telescope, the temperature is the same to within a few parts per 100,000. That uniformity is strange because, according to the standard Big Bang model without inflation, different regions of the early universe were never in contact with each other. They were too far apart. Light from one side of the observable universe would not have had time to reach the other side by the time the CMB was emitted. So how did those regions know to have the same temperature? How did they coordinate? You can't equilibrate a system if the parts of the system have never communicated. It's like expecting two people on opposite sides of the planet to synchronize their watches without ever meeting or sending signals. The standard model had no answer. The second problem was the flatness problem. Space, according to general relativity, can be curved. It can curve outward like the surface of a sphere, curve inward like a saddle, or be flat like a sheet of paper. The total energy content of the universe determines which shape space takes. If there's too much energy, space curves into a closed sphere, and the universe eventually collapses back on itself. If there's too little, space curves negatively, and the universe expands forever, accelerating as it goes. If the energy density sits exactly at a critical value, space is flat, and the expansion gradually slows but never quite stops. Observations tell us that our universe is flat, not approximately flat, extraordinarily flat, flat to within a fraction of a percent. That's weird because flatness is unstable. If the energy density at the beginning of the universe was even slightly off from the critical value, even by 1 part in 10 to the 60th, that deviation would have grown exponentially over time. If the early universe had been too dense, it would have collapsed within seconds. If it had been too sparse, galaxies would never have formed. The fact that we're here, in a universe that's still flat after 13.8 billion years, means the initial conditions had to be fine-tuned to a ridiculous degree. Again, the Standard Model had no explanation. It just shrugged and said the universe started that way. Deal with it. Guth realized that both problems could be solved with a single mechanism. If the universe went through a brief period of exponential expansion early on, that expansion would smooth out any initial lumpiness and stretch space so much that it would look flat, the same way the surface of a balloon looks flat if you blow it up large enough. The parts of the universe that are now far apart would have started out close together, in contact, able to reach thermal equilibrium before inflation kicked in and flung them across vast distances. One mechanism, 2 problems solved. Elegant. Here's how it works. In the very early universe, right after whatever came before the Big Bang, the dominant form of energy might not have been particles or radiation. It might have been something called a scalar field. Think of it as an energy field that fills all of space, kind of like an invisible fog with a certain energy density at every point. In Guth's model, this field was sitting in what physicists call a false vacuum. That's a state where the field has energy, but it's not in its lowest possible energy state. It's stuck, like a ball sitting in a shallow dip on a hillside. The ball wants to roll down to the bottom of the hill where it would have less potential energy, but it's temporarily trapped. While the field sits in that false vacuum, its energy density acts like a kind of anti-gravity. Instead of pulling things together the way normal matter does, it pushes space apart. And because the energy density stays roughly constant even as space expands, the pushing doesn't weaken. Normally, when the universe expands, matter and radiation get diluted. Spread the same amount of stuff over a larger volume and the density drops. But the energy in a scalar field doesn't dilute that way. As space expands, the field creates more energy to fill the new space. That sounds like it violates conservation of energy, and in a sense it does, but general relativity allows it, because the expanding space itself carries negative gravitational energy that exactly balances the positive energy of the field. The net energy stays zero. The result is runaway expansion. Double the size of the universe, and the energy density stays the same, so the expansion rate stays high, which doubles the size again, which keeps the energy density high, which doubles the size again. Exponential growth. In a tiny fraction of a second, a region smaller than a proton inflates to the size of a grapefruit, then a city, then a galaxy, then far larger than anything we can observe today. Eventually, the field rolls out of the false vacuum and drops into the true vacuum, its lowest energy state. When that happens, the energy that was driving inflation gets released. It converts into particles and radiation, reheating the universe and starting the hot Big Bang phase we're familiar with. Inflation ends, normal expansion takes over, and the universe continues evolving into what we see today. The inflationary period lasts maybe 10 to the minus 35 seconds. The reheating and everything after that, that's the 13.8 billion years. Inflation is the prelude. The Big Bang is the opening act. We're living in the long, slow denouement. Guth's original model had problems. The field didn't exit the false vacuum smoothly. It created bubbles of true vacuum that collided with each other in ways that would have left the universe lumpy and inhomogeneous, the opposite of what we observe. But within a couple of years, other physicists, notably Andrei Linde in the Soviet Union and Paul Steinhardt and Andreas Albrecht in the United States, refined the idea. They developed versions of inflation where the field rolls slowly and smoothly out of the false vacuum, producing a universe that's homogeneous and flat, exactly what we see. The basic mechanism stuck. Inflation became the leading explanation for why the universe looks the way it does on the largest scales. And the predictions it made, tiny fluctuations in the density of the early universe that would later seed the formation of galaxies, were confirmed by observations of the cosmic microwave background in exquisite detail. Inflation works, but inflation also does something no one expected. Once you accept that it happened, you have to deal with a deeply strange consequence. Inflation might not stop everywhere at once. In fact, in most versions of the theory, it doesn't. And if it doesn't stop everywhere, then it never really stops at all. It just keeps going, forever. Here's why. During inflation, the scalar field is rolling down from the false vacuum toward the true vacuum. But it's not rolling smoothly and deterministically like a ball rolling down a perfectly smooth hill. Quantum mechanics says that at very small scales, everything fluctuates. The field's value at any given point is subject to random quantum jitters. Most of the time, those jitters average out and don't affect the overall behavior. But during inflation, space is expanding so fast that those tiny quantum fluctuations get stretched to enormous sizes. A fluctuation that starts out smaller than a proton gets blown up to the size of a galaxy, then a supercluster, then larger. And some of those fluctuations push the field upward, back toward higher energy, even as the average field value is rolling downward. In most regions, the field wins the race and rolls all the way down to the true vacuum. Inflation ends, those regions reheat and become universes like ours. But in some regions, a quantum fluctuation kicks the field back up the hill. In those spots, inflation continues. And because inflation is exponential, those regions where it continues expand much faster than the regions where it stopped. The volume of space that's still inflating grows faster than the volume of space that has finished inflating. So even though individual regions are constantly dropping out of the inflationary phase and forming universes, the total amount of inflating space keeps increasing. Inflation becomes self-sustaining. It never ends. It's eternal. This is not a fringe idea. This is what the equations predict if you take inflation seriously and include quantum fluctuations. Alan Guth himself said it plainly. Once inflation starts, it almost certainly never stops. Not in the sense that our local region keeps inflating. Ours stopped 13.8 billion years ago. But somewhere else, far beyond anything we can observe, inflation is still running. And it's been running forever, and it will keep running forever, producing new universes constantly, an infinite cosmic factory. Each region where inflation ends becomes what physicists call a bubble universe. Our observable universe is one such bubble. From the inside, it looks like the whole universe. We see a Big Bang, a hot, dense beginning, 13.8 billion years of expansion, galaxies forming, stars lighting up, planets coalescing, us. But from the outside, if you could somehow step back and look at the larger structure, our universe is just one bubble in an endless foam. The bubbles don't interact, they're causally disconnected. Light from another bubble can never reach us because the space between the bubbles is inflating faster than light can cross it. Each bubble is a separate, self-contained universe with its own Big Bang, its own history, its own laws, potentially. And there are infinitely many of them. That last part is the kicker. If eternal inflation is correct, and if the underlying physics allows for different possible configurations of the scalar field or other fields that determine the properties of particles and forces, then different bubbles might end up with different physical constants. The strength of gravity might be different, the mass of the electron might be different, the number of spatial dimensions might be different. Most of those bubbles would be hostile to anything resembling life. A universe where gravity is too strong collapses immediately. A universe where the electromagnetic force is too weak doesn't form atoms. A universe with different masses for quarks doesn't produce stable protons. The vast majority of possible universes in this picture are sterile, empty, dead on arrival. But if there are infinitely many bubbles, and if the properties of each bubble are determined by random quantum fluctuations during inflation, then eventually, by pure chance, you'll get a bubble with properties that allow for stars, planets, chemistry, life. We live in one of those bubbles. Not because the universe was designed for us, but because we couldn't exist anywhere else. This is called the anthropic principle. It's not a prediction, it's an observation filter. We find ourselves in a universe that allows observers because universes that don't allow observers don't have anyone in them asking questions. This idea makes a lot of physicists deeply uncomfortable. For one thing, it's not testable. We can't see other bubbles, we can't measure their properties, we can't confirm they exist. Eternal inflation predicts an infinite multiverse, but it offers no way to check whether that prediction is correct. That's not how science is supposed to work. You're supposed to make predictions that can be tested and potentially falsified. If your theory predicts things that are in principle unobservable, how do you know it's not just speculation? For another thing, eternal inflation messes with probability. If there are infinitely many universes, and infinitely many of them are like ours, then any event that can happen will happen infinitely many times. There are infinitely many versions of you reading this right now, infinitely many where you stop reading halfway through, infinitely many where you never started. How do you do statistics in a framework like that? How do you calculate the likelihood of anything when every possibility occurs infinitely often? Physicists call this the measure problem, and it's been a thorn in the side of eternal inflation since the idea was first seriously considered. There's no agreed-upon way to make probabilistic predictions in an infinite multiverse. Different choices of how you count or weight the universes give you different answers, and there's no empirical way to decide which choice is correct. Then there's the question of whether inflation actually leads to eternal behavior in all models. Some versions of inflation naturally go eternal, others don't. It depends on the shape of the potential energy function for the scalar field, the details of how the field interacts with itself and other fields, and how you treat the quantum fluctuations. There are models where inflation ends everywhere after a finite time. There are models where it might go eternal in some regions but not others. The fact that eternal inflation is a generic prediction of many inflationary models does not mean it's a guaranteed feature of all of them. And since we don't know which model, if any, correctly describes the real universe, we don't know whether eternal inflation actually happens. But here's the thing, inflation itself is not in doubt. The observational evidence for a period of rapid exponential expansion in the early universe is overwhelming. The uniformity of the cosmic microwave background, the flatness of space, the pattern of tiny density fluctuations that match the predictions of inflation to absurd precision, all of that points to something like inflation having occurred. Eternal inflation is an extrapolation. It's what you get when you run the inflation equations forward and include quantum effects. It's not required by the observations, it's a consequence of the theory. And that makes it a very different kind of claim. Some researchers have argued that eternal inflation is actually less secure than people assume. In 2003, Arvind Borde, Alan Guth, and Alexander Vilenkin published a theorem, now called the BGV theorem, that showed any universe that's been expanding on average, including a universe undergoing eternal inflation, cannot be extended infinitely into the past. The theorem proves that if you follow the history of any inflating region backward in time, you eventually reach a boundary. You hit a point where the classical description breaks down. You need a quantum theory of gravity to go further. The BGV theorem doesn't say inflation had a beginning in the usual sense. It says the classical inflating spacetime is geodesically incomplete. There's a past boundary. What's on the other side of that boundary? The theorem doesn't tell you. But it does mean eternal inflation, despite the name, is not truly past eternal. It had to start somehow, somewhere, from something. Vilenkin himself has emphasized this point. Eternal inflation is eternal into the future, not the past. Once it gets going, it runs forever, generating endless universes. But the inflating phase itself had to begin. And explaining how it began, what came before the inflationary phase, that's still an open question. The BGV theorem closes one possible loophole. You can't avoid the question of cosmic origins by appealing to a process that's been running forever. Even eternal inflation had to start. So the question of what came first doesn't go away. It just gets pushed back one step. That said, eternal inflation does offer something valuable. It gives us a mechanism for producing a universe that looks fine-tuned without requiring actual fine-tuning. The standard Big Bang model says the initial conditions had to be set with extraordinary precision to get a universe like ours. The density had to be exactly right. The temperature had to be exactly right. The spatial curvature had to be exactly right. Why? No explanation. It just was. Eternal inflation offers a different answer. The conditions in our bubble universe are what they are because they were set by random quantum fluctuations during an inflationary phase that's generated countless other bubbles with different conditions. We're not special, we're just one outcome in an infinite set. The fine-tuning in our universe is an anthropic selection effect. We observe a universe compatible with our existence because incompatible universes don't have observers. That's not a completely satisfying answer. It replaces one mystery with another. Instead of asking why our universe has the properties it does, we're asking why the multiverse has the properties it does. Why does the underlying scalar field have the right kind of potential to drive inflation? Why do quantum fluctuations work the way they do? You've traded a fine-tuned universe for a fine-tuned multiverse generator, but at least you've moved the question to a different level, and some physicists find that progress. There's also the issue of whether the multiverse picture is fundamentally untestable. In principle, it might not be. Some versions of eternal inflation predict subtle patterns in the cosmic microwave background that could be signatures of collisions between bubble universes. If our bubble formed near another bubble and the two bubbles collided before moving apart, that collision could leave an imprint in the CMB, a slightly cooler or warmer spot in a particular direction. Several research groups have looked for such signatures. So far, they haven't found any. But the absence of evidence is not evidence of absence. It's possible the collisions are too rare, too faint, or washed out by other effects. Or it's possible they don't happen at all because the dynamics of bubble formation prevent collisions. The search continues. Even if we never find direct evidence for other bubbles, eternal inflation makes at least one testable claim. It predicts that our universe should look like a typical outcome of the inflationary process. If the theory is correct, most bubble universes should have certain statistical properties, and ours should match that distribution. If we found that our universe is sitting in some extraordinarily unlikely corner of the possible parameter space, that would be a problem for eternal inflation. So far, we don't see any red flags. Our universe looks reasonably generic given the constraints of being able to support observers. That's not proof the theory is right, but it's consistent with it. What eternal inflation really gives us is a shift in perspective. The Big Bang is no longer the origin of everything. It's a local event, a phase transition. The moment when one small region of an eternally inflating multiverse dropped out of the inflationary phase and began evolving according to the standard cosmological model. The 13.8 billion years is the age of that phase transition, not the age of the larger structure it's embedded in. And that larger structure doesn't have an age in the usual sense because it's been running forever into the future and, depending on how you interpret the BGV theorem, either had a beginning we don't yet understand or is embedded in something even larger that might not have a beginning at all. This is what modern cosmology has done to the idea of a cosmic origin. It's taken the straightforward story. The universe started 13.8 billion years ago with a hot, dense Big Bang, and turned it into a nested set of questions about what came before, what's outside, what's generating all of this, and whether any of those questions even make sense. Eternal inflation doesn't answer those questions, it reframes them. It moves the origin problem from our universe to the multiverse. And depending on how you look at it, that's either progress or evasion. But there are other ideas. Eternal inflation treats the Big Bang as a one-time event within each bubble, with no memory of what came before. But what if the universe doesn't just inflate forever into the future? What if it cycles? What if the Big Bang we observe is not the first expansion, but the latest in a series of expansions and contractions that have been running for far longer than 13.8 billion years? That's the cyclic model, and that's where the story goes next. Because if eternal inflation makes the Big Bang one event among infinitely many, a cyclic universe makes it one event in a repeating sequence. And in that framework, time doesn't begin, it just keeps going, again and again and again. Eternal inflation offers one way out of the singularity problem. It says the Big Bang wasn't the beginning of everything, just the beginning of our bubble. Somewhere else, inflation is still running, churning out new universes endlessly. But there's another possibility. One that doesn't require an infinite multiverse factory. One that doesn't push the origin back to some earlier inflating phase we can never see. What if the universe didn't start with a bang at all? What if it bounced? The Big Bang model describes what happened after the expansion began. It tells you how the universe cooled, how particles formed, how light decoupled from matter, how galaxies assembled. It's extraordinarily good at all of that. What it does not do, and has never done, is explain what came before. Standard cosmology treats the Big Bang as the starting point. Time begins there. Space begins there. Asking what happened before is, in the classical picture, like asking what's south of the South Pole. The question doesn't pass. There is no before, because time itself starts at the singularity. That's the official answer. It's also deeply unsatisfying, not because it's wrong, but because it's a non-answer. It's the equations throwing up their hands and saying, "We don't work here, stop asking." And physicists don't stop asking. The singularity is a mathematical artifact. Nobody believes the universe actually reached infinite density and infinite temperature. That's a sign the theory has hit its limits, not a description of reality. So if the singularity isn't real, what happened instead? What replaced it? One possibility is that the universe never got smaller than some minimum size, that instead of collapsing all the way down to a point, it reached a floor, a lower limit where quantum effects kicked in and stopped the collapse. And then, instead of sitting there frozen, it rebounded, it bounced. The universe transitioned from a contracting phase into the expanding phase we observe today. The Big Bang isn't the beginning, it's the turnaround point. The moment when a shrinking universe reversed course and started growing again. That's the Big Bounce. This is not a new idea. The concept of a bouncing universe has been around in various forms for decades, but it's been hard to make it work. General relativity doesn't allow bounces. If you run the equations backward, they drive you straight into a singularity. There's no mechanism in classical gravity to stop the collapse and reverse it. You need something else. You need quantum gravity. And for a long time, we didn't have a good quantum theory of gravity to work with. That started to change in the early 2000s with the development of something called loop quantum cosmology. Loop quantum cosmology, usually shortened to LQC, is a simplified version of loop quantum gravity applied to the universe as a whole. Loop quantum gravity is one of the leading approaches to building a quantum theory of space-time. The core idea is that space itself is not smooth and continuous at the smallest scales. It's made of discrete chunks, tiny loops of space woven together into a kind of quantum fabric. At everyday scales, this fabric looks smooth, the same way a piece of cloth looks smooth from a distance, even though it's made of individual threads. But zoom in far enough and the granularity shows up. Space becomes quantized. There's a smallest possible area, a smallest possible volume. You can't subdivide space infinitely. There's a floor. Loop quantum cosmology takes that framework and applies it to the early universe. And what it predicts is striking. When you include the quantum structure of space in your cosmological model, the singularity disappears, the equations don't blow up. Instead, they show that as the universe contracts and the density rises, quantum effects become stronger and stronger. At a certain point, when the density approaches something called the Planck density, about 10 to the 93rd grams per cubic centimeter, the quantum geometry of space creates an effective repulsive force, a kind of quantum pressure that opposes the collapse. The universe can't squeeze any smaller. The density hits a maximum and the collapse stops. Then the repulsion takes over and the universe bounces back into an expanding phase. No singularity, no infinite density, just a smooth transition from contraction to expansion, a big bounce. Martin Bojewald, a physicist who did much of the early work developing loop quantum cosmology in the mid-2000s, described it plainly. The universe exhibits a big bounce. The effective picture in loop quantum cosmology shows a scale factor, a measure of the universe's size, that reaches a minimum and then starts growing again. The bounce is not speculative. It's what the equations predict when you take the quantum nature of space-time seriously and apply it to the problem of the early universe. The singularity is replaced by a quantum bridge, connecting a contracting universe to an expanding one. This has profound implications. If the Big Bounce is real, then our universe is not the first. There was a universe before ours. A pre-Big Bang universe that was contracting, getting smaller and denser, until it hit the quantum limit and bounced into the expanding phase we're living in now. The 13.8 billion year clock doesn't measure the age of reality. It measures how long the current expansion phase has been running. Before that, there was a contraction phase, and before that, who knows, maybe another expansion. Maybe the universe cycles. Maybe it's been bouncing forever, oscillating between expansion and contraction in an endless rhythm with no beginning and no end. The bounce solves several problems at once. It eliminates the singularity, which is good because singularities are places where physics breaks, and we'd very much like to not have those sitting at the foundation of our cosmology. It provides a natural explanation for why the universe started expanding. In the standard model, the expansion just is. It's an initial condition. You accept it and move on. In a bouncing model, the expansion is the result of the bounce. The universe was contracting. It hit the quantum floor, and the bounce launched it into expansion. You've replaced a mysterious starting condition with a dynamical process. That feels like progress. It also offers a potential explanation for the uniformity and flatness of the universe without requiring inflation. Inflation was invented to solve the horizon problem and the flatness problem. It explains why the universe looks so smooth and why space is so flat by invoking a period of exponential expansion that stretched everything out. But inflation itself requires fine-tuned initial conditions. The scalar field has to start in the right state with the right energy density. You're solving one fine-tuning problem by introducing another. A bouncing universe offers a different route. In some bounce models, the contracting phase does the smoothing. As the universe shrinks, inhomogeneities get washed out. The universe enters the bounce in a smooth, flat state. Then the bounce flips the contraction into expansion, and you get a hot, dense, uniform Big Bang without needing inflation at all. The smoothing happens during the contraction, not during an inflationary burst after the bounce. That said, not all bounce models work that way. Some versions still include an inflationary phase after the bounce. Others rely on different mechanisms to explain the observed features of the universe. The point is that a bounce opens up new possibilities. It gives you another tool to work with. And in some cases, it lets you build models that are simpler or more natural than the standard inflationary picture. Loop quantum cosmology is the most developed bouncing framework, but it's not the only one. There are other approaches. String cosmology, which comes out of string theory, has its own version of a pre-Big Bang phase. In some string models, the universe starts in a cold, nearly empty state and slowly contracts, with the energy density rising over time. Eventually, the contraction reaches a point where stringy effects, the quantum behavior of the fundamental strings that are supposed to make up everything, become important. Those effects halt the collapse and trigger a transition into the hot expanding phase we observe. It's a different mechanism from loop quantum cosmology, but it leads to the same basic picture, a bounce connecting a pre-Big Bang contracting universe to our expanding one. Then there's the ekpyrotic scenario, a model developed in the early 2000s by a group including Paul Steinhardt, one of the key figures in inflationary cosmology. Ekpyrotic models involve extra dimensions and brane collisions. The idea is that our universe is a three-dimensional brane, a kind of membrane embedded in a higher dimensional space. There are other branes out there, and occasionally they collide. When two branes smash into each other, the energy of the collision heats up the branes and creates a hot, dense state that looks like a Big Bang from the inside. But it's not a beginning, it's a collision event. And the branes existed before the collision. They were moving through the higher dimensional space, getting closer, until they hit. After the collision, they bounce apart, cool down, and eventually gravity pulls them back together for another collision. The universe cycles. Each collision is a Big Bang. Each separation is a long period of expansion and cooling. The cycle repeats indefinitely. The ekpyrotic scenario is speculative. It requires extra dimensions, which we've never observed. It requires brains, which are theoretical objects from string theory that may or may not be real. But it's a worked-out model with equations and predictions. It's not hand-waving. And it makes a specific claim. What looks like a Big Bang is actually not. It's a bounce. That's Steinhardt's phrase, lifted almost verbatim from his explanations of the model. The Big Bang, in this picture, is a transition, a collision, a moment in a much larger cyclic process. All of these models, loop quantum cosmology, string cosmology, ekpyrotic scenarios, they share a common feature. They replace the singular beginning with a bounce, a moment of minimum size or maximum density where the universe transitions from contraction to expansion. And crucially, they all predict that information from the pre-bounce universe can, in principle, survive the bounce and show up in the universe we observe today. The bounce is not a reset button, it's a bridge, a narrow, violent, quantum-dominated bridge, but a bridge nonetheless. If that's correct, then the universe before the bounce is not completely inaccessible. It left fingerprints, and we might be able to find them. So what would those fingerprints look like? How do you test the idea that the universe bounced? The most promising place to look is the cosmic microwave background. The CMB is a snapshot of the universe 380,000 years after the Big Bang. The patterns in that snapshot, the tiny fluctuations in temperature and density, encode information about what was happening in the very early universe. In the standard inflationary picture, those fluctuations were seeded by quantum fluctuations during inflation. Random jitters in the inflaton field got stretched to cosmic scales and became the seeds of galaxies. Inflation makes very specific predictions about what the pattern of fluctuations should look like. The predictions match the data beautifully. That's why inflation is the leading model. But bounce models make different predictions. In a bouncing universe, the fluctuations are seeded during the contracting phase, not during inflation. The details depend on what's happening during the contraction. If the contraction is slow and smooth, you get one kind of fluctuation spectrum. If it's fast or turbulent, you get another. Some bounce models predict fluctuations that are nearly indistinguishable from the inflationary prediction. Others predict subtle differences, slightly different ratios of temperature fluctuations to density fluctuations, slightly different patterns in how the fluctuations are distributed across different scales. These are small differences, but they're potentially measurable. One key signature involves gravitational waves. Inflation predicts that it should have produced a background of primordial gravitational waves, ripples in space-time that have been propagating through the universe since the inflationary era. Those waves would leave a specific imprint in the polarization of the CMB, a pattern called B-modes. Detecting B-modes from inflation is one of the holy grails of observational cosmology. Several experiments are searching for them. None have found a definitive signal yet. Bounce models also predict gravitational waves, but the spectrum can be different. The amplitude, the frequency distribution, the way the waves interact with matter, all of those details depend on the dynamics of the bounce. Some bounce scenarios predict gravitational wave signatures that are stronger or shifted to different frequencies compared to inflation. If you could measure the gravitational wave background precisely enough, you might be able to distinguish a bounce from inflation. Another potential signature is in the large-scale structure of the universe. Bounce models, especially those that include a long contracting phase, can produce subtle anomalies in the distribution of galaxies and the clustering of matter, features that don't show up in the standard inflationary model. Some researchers have pointed to unexplained anomalies in the CMB, things like the cold spot or unexpected alignments in the temperature fluctuations, and suggested that they might be evidence of a bounce. The data is ambiguous. The anomalies are real, but they're not strong enough to rule out inflation. They're interesting hints, not smoking guns. The challenge is that most bounce models are hard to distinguish from inflation using current observations. The two frameworks make similar predictions for many of the things we can measure. Both produce a flat, homogeneous universe with a nearly scale-invariant spectrum of density fluctuations. Both can explain the large-scale structure we see. The differences are subtle. Detecting them requires extraordinarily precise measurements and careful modeling. And even if you find a deviation from the inflationary prediction, it's not automatic proof of a bounce. There are other explanations: modified inflation models, new fields, different physics during the early universe. Bouncing cosmology is one possibility among several. Then there's a deeper problem. Even if a bounce happened, it's not clear how much information from before the bounce could actually survive. During the bounce, the universe is in an extreme quantum state. Densities are at the Planck scale. Quantum fluctuations are enormous. The geometry of space-time itself is fluctuating wildly. In that environment, classical information, the kind of information encoded in the positions and velocities of particles, gets scrambled. Some models suggest that almost all information about the pre-bounce universe is erased. The bounce acts like a bottleneck. Only the most robust features, things encoded in the large-scale geometry or the quantum state of certain fields, make it through. Everything else is lost. A 2021 analysis published in Nature Physics took this idea seriously and ran the numbers. The authors looked at several pre-Big Bang models and asked how much information about fluctuations before the bounce could be extracted from observations of the CMB. Their conclusion was bleak. It is practically impossible to draw conclusions about fluctuations of the universe before the Big Bang using current data. The bounce suppresses the pre-bounce signal so much that even with perfect measurements, you couldn't say much about what the universe looked like before. The pre-Big Bang phase is effectively invisible. That doesn't mean the bounce didn't happen. It just means proving it happened is extraordinarily hard. But not everyone agrees with that assessment. Other researchers argue that certain observables, particularly gravitational waves and large-scale anomalies, are more robust and could carry clear signatures of the bounce. The debate is ongoing. What's clear is that bouncing cosmology is not a settled topic. It's a live research area with active theoretical work and ongoing searches for observational evidence. The fact that loop quantum cosmology predicts a bounce is significant. It's not an ad hoc feature added to avoid the singularity. It's a natural consequence of quantizing space-time. When you apply quantum mechanics to the geometry of the universe, the singularity goes away and a bounce appears in its place. That gives the idea a certain robustness. You're not just guessing that a bounce happened. You're deriving it from a framework that's trying to be a fundamental theory of quantum gravity. That said, loop quantum cosmology is still incomplete. The full theory of loop quantum gravity is incredibly complicated and not fully worked out. Most of the bounce results come from simplified models where you assume the universe is homogeneous and isotropic, the same in all directions, and you ignore complications like matter with complex equations of state or quantum fluctuations that feed back into the geometry. When you try to include those effects, the calculations get much harder and the results become less certain. Some studies have found that including quantum back reaction can make the bounce less clean or even destabilize it. The bounce is most robust in the simplest cases. Making it work in realistic scenarios is an ongoing challenge. Despite those challenges, the idea has momentum. Reviews of bouncing cosmologies, including a major one published in 2016, catalogue the progress that's been made and the problems that remain. The authors note that several different frameworks, loop quantum cosmology, string cosmology, ekpyrotic models, all converge on the same basic idea: a pre-Big Bang contracting phase followed by a bounce into expansion. The mechanisms differ, the details differ, but the overall structure is remarkably similar across different approaches. That convergence is suggestive. It suggests that maybe the universe really does work this way. Maybe the Big Bang really is a bounce. Maybe there was a universe before ours. If that's true, then the 13.8 billion year age is even less meaningful than eternal inflation made it. In eternal inflation, the 13.8 billion years is the age of our bubble in an infinite multiverse. In a bouncing universe, it's just the time since the last bounce. The universe itself could be far older, maybe infinitely old if the bounces keep happening. And that raises the same questions that eternal inflation raised. If the bounces go on forever, did they start? Is there a first bounce? Or does the cycle extend infinitely into the past as well as the future? Here's where things get tricky. You might think a cyclic universe avoids the problem of a beginning because it just cycles forever. No start, no end, just an eternal rhythm. But it's not that simple. The same theorem that complicates eternal inflation, the BGV theorem, also applies to cyclic models. If the universe has been expanding on average, even if it's been bouncing, then you can't extend the history infinitely into the past using classical spacetime. There has to be a boundary, a point where the classical description breaks down. You need quantum gravity to go further. The bounces can keep happening into the future indefinitely. But tracing them backward, you eventually hit a point where the cycle had to start, or where the concept of starting stops making sense because time itself becomes quantum and uncertain. That's not a fatal blow to bouncing cosmology. It just means the same issue that shows up in eternal inflation shows up here too. You can push the origin problem back, but you can't eliminate it entirely. Not with classical physics. Not even with sepsimasical quantum gravity. You need a full quantum theory of spacetime to say what happens at the boundary. And we don't have that yet. But what bouncing cosmology does offer is a concrete alternative to the standard story. It says the singularity is not real. The universe did not start from nothing. There was a prior state. A contracting universe that reached a quantum limit and bounced into the expanding phase we observe. That prior state had structure, it had matter and energy, it had geometry, and some of that structure might have survived the bounce and be encoded in the patterns we see in the CMB and the large-scale distribution of galaxies. We don't know yet. The observations aren't precise enough. But the idea is testable in principle, and that makes it science. The bounce also fits naturally with other ideas in quantum cosmology. If spacetime is fundamentally quantum, if there's a minimum size and a maximum density, then singularities shouldn't exist. They're artifacts of treating spacetime as classical. Replace the classical picture with a quantum one, and the singularities get smoothed out. The big bounce is one way that smoothing happens. It's not the only way, but it's one of the most developed, and it leads to a picture of the cosmos that's radically different from the one most people carry in their heads. The universe didn't begin, it transitioned. The Big Bang is not a creation event, it's a phase change. a moment when a shrinking universe reached its limit and started growing again. This is not settled science. Loop quantum cosmology is still being refined, the bounce models are still being tested, the observational signatures are still being hunted, but the framework is solid enough that serious physicists take it seriously. It's not fringe speculation, it's a live option. And if it's correct, then the question of what came before the Big Bang has a clear answer: another universe. A contracting universe that bounced into ours, and maybe before that, another bounce, and another. The cosmos as an eternal cycle of expansion and contraction, each phase seeding the next, no beginning, no end, just an infinite procession of universes unfolding one after the other. But there's another version of this idea that goes even further. Roger Penrose, the physicist who proved singularities are inevitable in general relativity, has proposed his own cyclic model, one that doesn't rely on bounces or quantum gravity, one that suggests the universe has been cycling not through bounces, but through something stranger. A sequence of cosmic epochs, each lasting trillions of years, each ending not in a collapse, but in an infinite expansion that somehow becomes the Big Bang of the next epoch. No bounces, no contractions, just an endless series of expansions, each one transforming seamlessly into the beginning of the next. That's conformal cyclic cosmology. And it takes the idea of a universe without a beginning in a completely different direction. Roger Penrose is not someone you ignore lightly. Nobel Prize winner for his work on black holes, the man who proved that singularities aren't just mathematical curiosities, they're inevitable features of general relativity. The physicist who worked alongside Stephen Hawking to map the boundaries of space-time and show that the universe, according to Einstein's equations, must have begun in a state of infinite density. Penrose knows the standard story inside and out. He helped write it. And then, in the mid-2000s, he proposed something so strange, so audacious, that even by the standards of cosmology, where people casually discuss multiverses and quantum foam, it turned heads. He called it Conformal Cyclic Cosmology, CCC for short. And it says the Big Bang wasn't the beginning. It was a recycling event. The universe has been here before, many times, and it will be here again, forever. The core claim is simple to state and almost impossible to wrap your head around. Penrose argues that the infinitely expanded, cold, empty future of one cosmic epoch, what he calls an Aeon, is mathematically identical to the hot, dense Big Bang of the next Aeon, not similar, identical. The far future and the distant past are the same thing, just viewed from different perspectives. When our universe has expanded for trillions upon trillions of years, when every star has burned out, every black hole has evaporated, and nothing is left but a thin soup of massless particles drifting through an ever-expanding void, that state can be conformally rescaled into the starting conditions of a new Big Bang. The end of one Aeon becomes the beginning of the next. No collapse, no crunch, no bounce, just a smooth transition from infinite future to fiery start. The universe doesn't reset, it continues. An endless chain of aeons stretching backward and forward in time, with no first moment and no final moment, just an eternal cycle. This is not a bouncing universe in the sense we just discussed. There's no contraction phase. The universe doesn't shrink back down and hit some quantum floor that kicks it into a new expansion. CCC works entirely within the framework of classical general relativity. Penrose isn't appealing to quantum gravity or exotic new physics. He's using the equations we already have and showing that they allow for something nobody expected, a way for the universe to age infinitely and yet begin again. The mechanism is conformal geometry, and that's where things get technical, but stay with it because this is the heart of the idea. In mathematics, a conformal transformation is a change that preserves angles but not distances. Imagine you have a map of a city. If you zoom in, the streets and intersections keep their shapes, but the scale changes. A conformal map does something similar. It stretches or shrinks space while keeping the local geometry intact. The shapes of things, the relationships between nearby points, those stay the same. What changes is the overall size. General relativity describes spacetime using something called the metric, a mathematical object that tells you how to measure distances and intervals between events. Different metrics describe different spacetimes. But some metrics, even though they describe very different physical situations, are conformally equivalent. They have the same local structure, just at different scales. Penrose realized that the metric describing the far future of an expanding universe and the metric describing the early moments after a Big Bang are conformally equivalent. They're the same shape. The difference is just a matter of scale. And if you're clever about how you handle that scale, you can erase it entirely. Here's the trick. In the far future, the universe is cold, empty, and expanding. All the matter that hasn't already decayed or been pulled into black holes is long gone. What's left is radiation, photons, maybe some massless neutrinos if those turn out to be massless, which is still an open question. The key point is that in the extreme late universe, everything that remains is massless, and massless particles don't experience time the way we do. From the perspective of a photon, the journey from one end of the universe to the other takes zero time. Photons don't have clocks, they don't age. The far future, from the perspective of the particles that inhabit it, is timeless. It's a state where the concept of duration stops meaning anything. Now compare that to the very early universe, right after the Big Bang. The universe is hot, dense, and dominated by radiation. Matter hasn't formed yet. Everything is moving at or near the speed of light. The particles are massless, or effectively massless, because their thermal energy is so high that their rest mass is negligible. Again, you have a state dominated by radiation, by particles that don't experience time. The geometry is different, the density is different, but the local structure, the way light cones are arranged, the causal relationships between events, those are conformally equivalent to the far future. Penrose argues that you can take the metric describing the infinite future and apply a conformal transformation that makes it look exactly like the metric of a new Big Bang. The universe, he says, loses track of how big it is at the transition between aeons. Size becomes meaningless in a radiation-dominated, timeless state. And without a well-defined scale, the infinitely large and the infinitely small become indistinguishable. This is not just philosophy. Penrose has written down the equations. He's shown that you can match the boundary of one aeon, the point where time goes to infinity and the universe has expanded without limit, to the starting point of the next aeon, the moment of the Big Bang. The matching isn't perfect. There are details to work out, conditions that have to be satisfied, but the framework is there. You can construct a spacetime that cycles through aeons, each one lasting an infinite amount of time from the perspective of observers inside it, yet transitioning smoothly into the next. The cycle is eternal, no beginning, no end. Just an endless succession of cosmic epochs, each one indistinguishable from the others in structure, yet unique in the particular details of how matter and energy are distributed. Penrose's motivation for proposing this comes from several places. One is philosophical. He's never been comfortable with the idea of an absolute beginning. The singularity at the start of the Big Bang is, in his view, a sign that the theory is incomplete. General relativity predicts a singularity, and Penrose proved that rigorously in the 1960s, but he also suspects that the singularity is not the whole story. There should be a way to extend the theory, to smooth out the singularity without invoking exotic quantum gravity effects that we can't test. CCC is his attempt to do that using the classical framework. Another motivation is observational. The standard Big Bang model, even with inflation, requires finely tuned initial conditions. The universe starts out in a very specific state, low entropy, highly uniform, with just the right amount of energy density to produce the flat, smooth cosmos we observe. Why did it start that way? The usual answer is that inflation set it up. But inflation itself requires special conditions. The inflaton field has to be in the right state. The energy density has to be just so. You're explaining one set of fine-tuned conditions by appealing to another. Penrose finds that unsatisfying. He thinks the initial conditions of our Aeon, the state the universe was in right after the Big Bang, should be explained by what came before. And in CCC, what came before is the previous Aeon. The smooth, low-entropy start of our universe is a natural consequence of the high-entropy, radiation-dominated end of the prior Aeon. The transition wipes the slate clean in some respects, resetting the clock. But it doesn't require any special setup. It's just what happens when the universe runs its course. There's also a practical reason. If CCC is correct, it makes predictions. Specific, testable predictions about patterns we should see in the cosmic microwave background. Penrose and his collaborators have argued that information from the previous Aeon doesn't completely vanish. Some of it survives the transition and shows up as subtle anomalies in the CMB. The most dramatic of these are what Penrose calls Hawking points. These are localized hotspots in the CMB that are predicted to form from the final evaporation of supermassive black holes in the previous Aeon. Here's how that works. In the late stages of an Aeon, long after all the stars have died, the universe is dominated by supermassive black holes. These are the monsters that sit at the centers of galaxies, some of them weighing billions of times the mass of the Sun. They don't last forever. Stephen Hawking showed in the 1970s that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation is incredibly faint, but over unimaginably long timescales, it causes the black hole to lose mass. Eventually, the black hole evaporates completely. The process takes an absurdly long time. A supermassive black hole with a mass of 10 billion suns would take something on the order of 10 to the power of 106 years to evaporate. That's a 1 followed by 106 zeros. A number so large it makes the current age of the universe, a mere 13.8 billion years, look like the blink of an eye. But in CCC, that timescale doesn't matter. The Aeon lasts forever. There's no rush. Eventually, every black hole evaporates. And when it does, the energy released during the final moments of evaporation, the explosive burst, as the last bit of mass converts to radiation, creates a disturbance in the surrounding spacetime. That disturbance, Penrose argues, survives the transition to the next Aeon. It shows up as a hotspot, a small region in the new universe where the energy density is slightly higher than average. By the time the universe has cooled enough for the CMB to form, about 380,000 years after the Big Bang, that hotspot is still there. It registers as a localized warm patch in the microwave background, a Hawking point. Penrose and his team published a paper claiming they had found evidence of these points in the actual CMB data. They identified specific spots in the sky where the temperature was higher than the surrounding average, in a pattern consistent with what you'd expect from a black hole evaporation event in a prior aeon. The announcement generated a lot of attention. If true, it would be the first direct evidence that the universe existed before the Big Bang, that something from a previous cosmic epoch had left a mark we could detect. It would be huge. The problem is that the evidence is shaky. Other researchers have looked at the same data and come to different conclusions. Independent reanalysis found that the spots Penrose identified are not statistically significant. They're within the range of what you'd expect from random fluctuations in a standard cosmology. The CMB is full of hot spots and cold spots. It's not uniform. Finding a few that happen to line up with the pattern you're looking for doesn't prove your model is correct, especially when there are thousands of spots to choose from and you're picking the ones that fit. This is a classic problem in data analysis. If you search long enough through a large dataset, you'll find patterns, but those patterns might just be noise. You need a rigorous statistical test to determine whether the signal you're seeing is real or whether it's an artifact of how you're searching. The consensus among cosmologists is that the Hawking point claim has not held up. The signal is weak, the statistics are ambiguous, and the standard Big Bang model with inflation can explain the features Penrose found without invoking a previous aeon. That doesn't mean CCC is wrong. It just means this particular piece of evidence isn't as solid as initially claimed. Penrose and his collaborators continue to refine their analysis, looking for stronger signals and better ways to distinguish CCC predictions from standard cosmology. But as of now, the Hawking points remain unconfirmed. There's another predicted signature: concentric circles in the CMB. These are thought to arise from collisions or close encounters between supermassive black holes in the previous aeon. When two black holes orbit each other and eventually merge, they emit gravitational waves. In the late stages of an aeon, when the universe is old and empty, these mergers would still be happening. The gravitational waves they produce would ripple through space-time, and those ripples, like the Hawking radiation from evaporating black holes, might survive the transition to the next aeon. They would show up as circular patterns in the CMB, rings of slightly correlated temperature fluctuations. Penrose and his colleagues reported finding such circles in the data. Again, the claim generated interest. And again, independent analysis failed to confirm it. The circles, other researchers found, are consistent with what you'd expect from random chance in a standard cosmological model. The evidence is not compelling. This is frustrating for supporters of CCC. The theory makes predictions. It tells you what to look for. But when you go looking, the signals either aren't there or they're too weak to distinguish from noise. That doesn't disprove the theory, but it doesn't help either. Science progresses when theories make sharp predictions that turn out to be correct. When the predictions are fuzzy or when the data is ambiguous, you're stuck in a gray zone. CCC is currently in that gray zone. It's a serious idea with real math behind it, but the observational support is lacking. The signatures it predicts are subtle. The data we have is noisy, and the statistical tools we use to analyze the data are prone to false positives if you're not careful. Despite these challenges, CCC is still being actively developed. A 2025 paper, just published recently, works through the details of the conformal crossover surface, the mathematical boundary where one aeon transitions into the next. The authors show that the surface is conformally smooth except at discrete Hawking points, which appear as tiny singularities in the conformal structure. This is progress. It's refining the model, making it more precise, addressing technical objections. The fact that people are still working on CCC 3 decades after Penrose first proposed it in the mid-2000s, with the widely cited account putting the proposal around 2005, tells you it's not been dismissed as fringe nonsense. It's taken seriously enough that researchers are putting in the effort to test it and improve it. The philosophical implications of CCC are profound. If the model is correct, then the universe has no beginning. Not in the sense that time stretches back infinitely into the past in a simple linear way, but in the sense that every aeon is both a beginning and an end. Each Big Bang is the continuation of a previous aeon's infinite expansion. The cycle is eternal. You can trace the history backward through one aeon, then another, without ever hitting a first moment. There's no starting point, no creation event. Just an endless succession of cosmic epochs, each one emerging from the one before it. This fits with Penrose's broader view of the universe. He's always been suspicious of the idea that the laws of physics themselves came into being at the Big Bang. Laws, in his view, are timeless. They don't have a beginning, they just are. CCC offers a cosmology that matches that intuition. The universe has always existed in some form. The particular aeon we're in now, the one that started 13.8 billion years ago, is not the first. It's not special. It's just the current iteration of a process that's been running forever and will keep running forever. The cosmos recycles itself. Matter and energy are reshuffled with each transition, but the underlying structure, the laws, the geometry, those remain constant. The universe is eternal, not because it sits static and unchanging, but because it continually renews itself. That said, CCC has its critics. Some point out that the conformal rescaling Penrose uses is a mathematical trick that only works if certain conditions are met. The late universe has to be dominated by massless particles. If there's any residual matter with mass, even a tiny amount, the trick doesn't work. You can't erase the scale factor. The transition breaks down. Penrose argues that in the extreme late stages of an aeon, all matter decays or falls into black holes and then evaporates as Hawking radiation. What's left is pure radiation, which is massless. But critics point out that we don't know for sure that protons decay. The current experimental limits say protons have a lifetime longer than 10 to the 34 years, but we haven't proven they decay at all. If they don't, then in the far future, there will still be protons floating around, and those have mass. The conformal trick fails. Penrose's response is that even if protons are stable, they would eventually fall into black holes or be so diluted by the expansion that their contribution to the energy density becomes negligible. The universe, he argues, asymptotically approaches a radiation-dominated state regardless of whether individual particles decay. Whether that argument holds up is still debated. Another criticism is that CCC doesn't explain why the universe is in the cyclic state it's in. If the aeons have been cycling forever, why are they stable? Why doesn't the transition process break down after a finite number of cycles? Why doesn't entropy pile up in a way that eventually grinds the cycle to a halt? These are hard questions. Penrose has answers, but they're not universally accepted. The entropy issue is particularly thorny. In each aeon, entropy increases. That's the second law of thermodynamics. The universe gets more disordered over time. But at the transition to the next aeon, the entropy is somehow reset, or at least redistributed in a way that allows the new aeon to start in a low entropy state. How does that happen? Penrose argues that the conformal rescaling effectively wipes out the memory of the high entropy from the previous aeon. The new aeon starts fresh. But it's not clear that the math actually supports that. Some analyses suggest that entropy should accumulate across aeons, which would make the cycle unsustainable. If that's true, then CCC can't run forever into the past. It would have to start at some finite time, which brings you back to the question of what came before the first aeon. There's also the issue of quantum mechanics. CCC is a classical theory. It's built on general relativity, which is deterministic and continuous. But we know the universe is quantum. At small scales, things fluctuate. Particles pop in and out of existence. The geometry of space-time itself should be subject to quantum uncertainty. Penrose is well aware of this. He's spent much of his career thinking about quantum mechanics and its relationship to gravity. But CCC, as currently formulated, doesn't incorporate quantum effects in a fundamental way. It treats space-time as smooth and classical. That's fine for describing the large-scale structure of the universe, but it means CCC has nothing to say about what happens at the Planck scale, where quantum gravity effects should dominate. If the transition between aeons involves regions of extremely high curvature or energy density, even briefly, then quantum effects can't be ignored. You'd need a quantum version of CCC to describe what's really going on. Penrose has ideas about that, but the quantum theory isn't fully developed. Still, CCC is an impressive piece of theoretical work. It takes the equations of general relativity seriously and pushes them to their logical conclusion. It shows that a cyclic universe is possible without invoking exotic new physics. It makes testable predictions, even if those predictions haven't been confirmed yet. And it offers a genuinely different perspective on the problem of cosmic origins. Most models treat the Big Bang as a special event that requires explanation. CCC says the Big Bang is just a transition point. It's not special. It's not the beginning. It's a moment in an eternal process. The real story isn't about how the universe started, because it didn't start. The real story is about how it keeps going, how it renews itself, how it transforms an ending into a beginning without ever stopping. That shift in perspective is valuable even if CCC turns out to be wrong. It forces you to think differently about time, about entropy, about what it means for the universe to have a history. It challenges the assumption that there was ever a first moment, and it opens up space for other ideas that don't treat the Big Bang as an absolute boundary. CCC is one route toward a beginningless cosmos, but it's not the only one. There are other proposals that also try to eliminate the singularity and extend the history of the universe backward indefinitely. Some of them, like the bouncing models we discussed earlier, rely on quantum gravity. Others take a different approach entirely. One of the most famous is Stephen Hawking's no-boundary proposal, a model that says time didn't start at the Big Bang because there's no sharp boundary between time and space at the beginning. The universe, in Hawking's picture, doesn't have a starting point. Not because it cycles or bounces, but because the concept of a starting point dissolves when you treat time itself as a quantum variable. That idea is radically different from CCC. It doesn't involve aeons or conformal rescaling or black hole evaporation. It involves imaginary time and the idea that the universe can be finite in extent yet have no edge. It's strange, it's subtle, and it's where the conversation goes next. Because if Penrose's answer to the origin problem is that the universe has always been here in one form or another, Hawking's answer is that the question of when the universe began doesn't even make sense. The two approaches couldn't be more different, but they both lead to the same conclusion. Time, as we usually think of it, doesn't have a beginning. The 13.8 billion year age is a marker, a milestone in the history of the observable universe, but it's not the start of everything. And once you accept that, the whole idea of cosmic origins starts to look very different. Stephen Hawking thought the universe might not have a beginning the way most people imagine it. Not because it cycles, not because it bounced, not because there was some earlier phase we can't see, but because the question itself, when did the universe begin, might not pass the way we think it does. The Big Bang, in Hawking's picture, is not a moment when time started ticking. It's a place where time changes shape, where the dimension we call time smoothly curves into something that looks more like space, and the whole idea of a first instant dissolves. No boundary, no edge, no moment before which there was nothing, just a universe that's finite in extent but has no point you can call the start. That's the no-boundary proposal, and if it's correct, the question of what came before the Big Bang is not unanswered. It's meaningless. The same way asking what's south of the South Pole is meaningless. Not because we don't know the answer, but because the question assumes a geography that doesn't exist. Hawking didn't come up with this idea alone. He developed it in the early 1980s in collaboration with James Hartle, a physicist at the University of California, Santa Barbara. The core paper was published in 1983, but Hawking had started talking about the concept publicly a bit earlier, including at a Vatican conference in 1981, where he laid out the rough framework. That Vatican talk became famous, not just for the physics, but for the setting. Here was one of the world's leading cosmologists, presenting to an audience that included Catholic theologians, explaining a model of the universe that had no need for a moment of creation. The Pope was in attendance. The stakes, at least symbolically, were high. Hawking's punchline, the thing he kept repeating in various forms over the years, was deceptively simple. There ought to be something very special about the boundary conditions of the universe. And what can be more special than the condition that there is no boundary? The boundary he's talking about is the edge of time. In the standard Big Bang picture, you run the clock backward and eventually you hit a singularity, a point where the density and temperature become infinite and the equations break down. That singularity is a boundary in the mathematical sense. It's the place where space-time ends or begins, depending on which direction you're looking. And it's a problem because general relativity doesn't tell you what happens at the boundary. You need extra information. You need to specify the initial conditions. What was the universe's state at the singularity? What was the density, the temperature, the curvature? The standard model doesn't give you those answers. It just says, pick some values and see what happens. That's unsatisfying. You're explaining the universe by assuming a very specific starting configuration, and you have no way to explain why the universe started in that configuration rather than some other one. Hawking and Hartle wanted to eliminate the need for initial conditions entirely. If you could get rid of the boundary, the singularity, the edge of time, then you wouldn't have to specify what the universe was like at the beginning, because there would be no beginning. The universe wouldn't start, it would just be. And the way they proposed to do this involved a concept that sounds like science fiction, but is actually a standard tool in theoretical physics: imaginary time. Before we get to imaginary time, let's talk about what time actually is in the context of general relativity. Time is a dimension. That's not a metaphor. In Einstein's theory, space-time is a four-dimensional structure. 3 dimensions of space, 1 of time. Events in the universe are points in this 4-dimensional space. Your location is specified by 3 spatial coordinates, where you are, and 1 temporal coordinate, when you are. The geometry of space-time, the way distances and intervals are measured, is described by something called the metric, and crucially, the metric treats time differently from space. The mathematical formula that defines the space-time interval, the measure of separation between two events, has a minus sign in front of the time term. That minus sign is what makes time distinct from space. It's what gives time its arrow, its directionality. Space is something you can move through forward or backward. Time, at least in classical physics, only goes one way, but there's a trick you can do. If you replace the time coordinate with an imaginary number, a number involving the square root of -1, the minus sign in the metric goes away. The time dimension starts to look like just another space dimension. The four-dimensional space-time becomes a four-dimensional space. There's no preferred direction, no arrow, no distinction between past and future. This is called Euclidean time, or sometimes imaginary time. It's a mathematical device. Physicists use it all the time in quantum field theory because it makes certain calculations easier. You do your work in imaginary time, figure out what you need to figure out, and then transform the results back to real time at the end. It's a tool, a trick. Nobody thinks imaginary time is real in the sense that you could experience it or measure it directly. It's a way of doing math. Hawking and Hartle took this trick and applied it to the entire universe. In their model, the early universe, very close to what we would call the Big Bang, is described not with ordinary time, but with imaginary time. And in imaginary time, the distinction between time and space disappears. The geometry near the origin of the universe is smooth. There's no singularity because there's no sharp boundary where time begins. Instead, time gradually curves into space. The universe doesn't have a starting point any more than the surface of the Earth has a southernmost point once you reach the South Pole. That's the analogy Hawking used over and over, and it's the right one to understand what's going on. Imagine you're standing at the equator and you start walking south. You're moving along a line of longitude, heading toward the South Pole. As you walk, your latitude changes. You go from 0 degrees at the equator to 10 degrees south, 20 degrees, 30, and so on. The further south you go, the closer you get to 90 degrees south, the South Pole itself. Now here's the question. What happens when you reach the South Pole? What's south of the South Pole? The answer is nothing. Not because there's a wall or an edge, but because once you're at the pole, the concept of south stops making sense. There's no further south to go. Every direction from the South Pole is north. The pole isn't a boundary, it's just a point on the surface of a sphere. You can keep walking if you want. You'll start heading north, but there's no moment where you hit the edge of the Earth and have to stop. The geometry is smooth, the surface continues, there's just no more south. The no boundary proposal applies the same logic to time. If you run the clock backward from today, you're moving toward the Big Bang. The universe is getting smaller, hotter, denser. Eventually, you reach a point where the classical description breaks down, and you need quantum mechanics. That's where Hawking switches to imaginary time. In imaginary time, the dimension we call time behaves like a spatial dimension. The geometry is smooth and round, like the surface of a sphere. And just as there's no point on Earth that's the southernmost point beyond which nothing exists, there's no point in this geometry that's the earliest moment beyond which nothing exists. The universe doesn't have a boundary in time. You can trace the history backward as far as you want, and the geometry just curves smoothly. There's no singularity, no moment when time starts, no edge. Now, what does this actually mean physically? That's where things get slippery. Hawking was always careful, at least in his technical papers, to emphasize that imaginary time is a mathematical tool. You use it to calculate the quantum state of the universe, to figure out the probability of the universe being in a particular configuration. Once you've done that calculation, you transform back to real time and describe the evolution of the universe in the usual way. The imaginary time part is the scaffolding. You build with it, then take it down when you're done. But in his popular writing, especially in A Brief History of Time, Hawking sometimes blurred the line. He talked about imaginary time as if it might be as real as ordinary time, just harder to observe. He suggested that maybe in the very early universe, time really did behave like a space dimension, and only later, as the universe expanded and cooled, did it take on the properties we recognize. That's a bolder claim. It's saying imaginary time isn't just a calculational trick. It's a description of what actually happened. Whether Hawking fully believed that interpretation, or whether he was just trying to make the idea accessible to a popular audience, is hard to say. He was a brilliant communicator, but also a provocateur. He liked to push ideas to their logical extremes and see how people reacted. What's clear is that the no-boundary proposal, taken seriously, has profound implications. If the universe has no boundary in time, then it doesn't need a cause. It doesn't need something to set it in motion. It doesn't need initial conditions specified by some external agent. The universe is self-contained. Its history is determined entirely by the laws of physics, with no need for anything outside the system to explain how it got started. Hawking said it explicitly. The boundary conditions of the universe are that it has no boundary. That's not a cop-out. That's a statement about the structure of space-time. The universe doesn't begin in time because time itself curves into space at the origin. You can't ask what came before because there is no before. The geometry doesn't allow for it. This resolves one of the deepest puzzles in cosmology. If the Big Bang is a moment when the universe came into existence, you immediately face the question of what caused it. What set the clock ticking? What determined the initial conditions? Physicists hate those questions because they sound dangerously close to theology. And if you're trying to build a scientific theory, you don't want to have to appeal to something outside the laws of nature to explain the starting point. The no-boundary proposal offers a way out. It says the universe doesn't have a starting point. It's finite in time, meaning you can't trace the history back infinitely far, but it's unbounded, meaning there's no edge or boundary where you have to stop and say, this is where it began. The universe is like the surface of a sphere, finite in area, but with no edge. You can walk around it forever and never fall off or hit a wall. That analogy works well for the spatial part of the geometry. But applying it to time is where people struggle. We experience time as having a direction: past, present, future. We remember the past, not the future. We can influence the future, not the past. That's not just psychology. It's baked into the laws of thermodynamics. Entropy increases over time. Systems move from order to disorder. The arrow of time is real. So what does it mean to say that near the Big Bang, time becomes space? How do you reconcile the smooth, directionless geometry of imaginary time with the one-way flow of ordinary time? Hawking's answer is that the transition happens smoothly. In the very early universe, described in imaginary time, there's no arrow, no distinction between past and future. But as the universe expands and evolves, it transitions into real time, and the arrow emerges. Entropy starts increasing. The distinction between past and future becomes meaningful. The no-boundary proposal doesn't get rid of the arrow of time. It just says the arrow doesn't extend all the way back. Near the origin, the geometry is timeless. Further out, time behaves the way we expect. The universe has a finite age in the sense that you can only trace the history back so far before the geometry rounds off and the concept of earlier stops making sense. But it's not infinite in age either. You can't extend the timeline backward forever. There's a natural limit, a cap, and that cap is smooth and round, not sharp and singular. This is mathematically elegant. It's philosophically bold. It's also incredibly hard to test. The no-boundary proposal makes predictions, but they're subtle and involve the quantum state of the universe, something we can't directly observe. In principle, the proposal predicts certain features in the distribution of matter and energy in the very early universe, which in turn would affect the patterns we see in the cosmic microwave background. Some studies have tried to work out what those predictions are and compare them to the data. The results have been mixed. The no-boundary proposal doesn't obviously contradict the observations, but it also doesn't make sharp, distinctive predictions that clearly set it apart from other models. You can tweak the details, adjust the parameters, and get a range of outcomes. That flexibility makes the idea hard to falsify. And in science, if you can't falsify something, you're in murky territory. There's also a deeper problem. The no-boundary proposal is built on quantum cosmology, the application of quantum mechanics to the universe as a whole. And quantum cosmology is a field that's still very much under construction. We don't have a complete, universally accepted theory of quantum gravity. We have candidates, string theory, loop quantum gravity, others, but none of them have been tested experimentally. The no-boundary proposal assumes you can write down something called the wave function of the universe, a quantum description of all possible configurations of spacetime, and calculate probabilities for different outcomes. That's a bold assumption. It's not clear that the wave function of the universe is even a well-defined concept. Some physicists argue that quantum mechanics only makes sense when you have an observer outside the system, measuring it. But if the system is the entire universe, there's no outside. There's no observer standing apart from the system. So how do you interpret the wave function? What does it mean to assign probabilities to different universes when there's only one universe and no external vantage point to observe it from? These are not just technical quibbles, they're foundational issues that go to the heart of what quantum mechanics is and how it applies to cosmology. Hawking was aware of the problems. He spent much of his later career thinking about them. He proposed various interpretations and refinements, but he never fully resolved the tension. The no-boundary proposal remains a framework, not a finished theory. It's a way of thinking about the origin of the universe that avoids certain pitfalls, but it introduces new questions in their place. One thing the no-boundary proposal does not do is prove the universe had no cause or no creator. Hawking sometimes framed it that way in his popular writing, suggesting that the model left no room for a divine hand to set things in motion. But that's more rhetoric than rigorous argument. The no-boundary proposal shows that you don't need to invoke anything outside the laws of physics to explain the origin of the universe if those laws include quantum gravity and imaginary time. But where do the laws come from? Why does the universe obey those particular laws and not others? The proposal doesn't answer that. It assumes the laws and shows that given those laws, the universe can be self-contained. That's impressive, but it's not the same as explaining why there's something rather than nothing, or why the laws of nature are what they are. Those questions remain open. Another angle to consider is the role of the wave function. In the no-boundary proposal, the quantum state of the universe is determined by a specific rule. You integrate over all possible smooth, closed geometries in imaginary time. That integration picks out a particular wave function, which then determines the probabilities for different configurations of the universe in real time. The rule is simple and elegant. It's the rule that says the universe has no boundary. But it's still a rule. You're still putting in a condition, a principle, a choice about how to calculate the wave function. Hawking's claim is that this is the most natural choice, the simplest possible boundary condition, and maybe he's right. But it's not the only choice. You could imagine other rules, other ways of specifying the wave function that lead to different outcomes. So in some sense, the no-boundary proposal doesn't eliminate the need for initial conditions. It just replaces an arbitrary specification of what the universe was like at time zero with an arbitrary specification of what rule you use to calculate the wave function. That's progress, arguably, but it's not a complete elimination of the problem. The no-boundary proposal also has implications for the multiverse, though this wasn't Hawking's main focus. If the universe's quantum state is described by a wave function that includes all possible geometries, then, in a sense, all those geometries exist in the quantum superposition. You have a universe that's in a state of being many different configurations at once, until some kind of observation or decoherence process picks out one of them. That sounds like a multiverse, a quantum multiverse, where all the possible histories are real in some sense. But again, interpreting what that means physically is tricky. Hawking generally avoided strong multiverse language in the context of the no-boundary proposal. He focused on the idea that the proposal gives you a specific, well-defined quantum state for our universe. Whether other universes exist in some parallel sense was not the main point. Over the years, the no-boundary proposal has been both celebrated and criticized. Celebrated because it's a bold, original idea that tackles one of the hardest problems in physics. Criticized because it's built on shaky foundations and makes predictions that are hard to test. Some researchers have tried to refine it, to work out the details more carefully and see if it really holds up under scrutiny. Others have pointed out potential flaws. One major issue is the measure problem again, the same problem that plagues eternal inflation. If you're calculating probabilities over all possible geometries, how do you weight them? How do you count? Different choices give different answers, and there's no clear way to decide which choice is correct. That ambiguity undermines the predictive power of the proposal. Another issue is whether the transition from imaginary time to real time is physically meaningful or just a mathematical trick. If it's just a trick, then the no-boundary proposal is a way of doing calculations, but it doesn't tell you anything deep about the nature of time. If it's physically meaningful, then you need to explain what it means for time to change character, to go from being space-like to being time-like. That's a strange kind of phase transition. It's not clear what drives it or what it would look like if you could observe it. Despite these challenges, the no-boundary proposal has had a lasting impact on cosmology. It showed that you can think about the origin of the universe without requiring a singularity or a first moment. It introduced imaginary time as a tool for quantum cosmology. It inspired a generation of physicists to take seriously the idea that the universe might be self-contained, that the laws of physics might be enough to explain not just how the universe evolves, but how it came to be in the first place. Whether the specific proposal Hawking and Hartle put forward in 1983 is correct is still an open question. But the broader idea that the universe might not have a beginning in the traditional sense has become a serious part of the conversation, and that's the shift that matters. For most of human history, the question of cosmic origins was a question for religion or philosophy. Science couldn't touch it because science deals with processes and mechanisms, and if you push back to a first moment, you run out of processes to study. You hit a wall. The no-boundary proposal, like the bouncing models and eternal inflation and conformal cyclic cosmology, says maybe there is no wall. Maybe the origin problem is a problem we created by assuming time has to have a starting point. Maybe the universe is structured in a way that makes the concept of a first moment nonsensical. The geometry curves. The dimension we call time blends into space. The boundary disappears. And what you're left with is a cosmos that's finite, bounded, self-contained, and yet has no edge in time, no moment you can point to and say, this is where it all began. Hawking summarized the idea in his trademark style. If the universe is really completely self-contained, having no boundary or edge, it would neither be created nor destroyed. It would simply be. That's from A Brief History of Time. Simple words, huge implications. If the universe simply is, if it doesn't need a starting point or an external cause, then the whole framework of creation cosmology falls apart. You don't need a creator. You don't need a first cause. The universe explains itself. The laws of physics plus the no-boundary condition are enough. That's a radical claim. It's also a deeply appealing one if you're trying to build a purely scientific account of reality. No miracles, no gaps, just physics all the way down. But here's the uncomfortable truth. Even if the no-boundary proposal is correct, it doesn't settle the question of whether the universe had a beginning. It settles the question of whether time had a beginning. Those are different. The proposal says time doesn't extend infinitely into the past and doesn't have a sharp starting edge. Time is finite but unbounded. That's a specific structure. But it doesn't tell you whether the universe, the physical reality described by space-time, exists eternally in some larger sense, or whether it popped into existence as a quantum fluctuation, or whether it's embedded in a multiverse, or something else entirely. The no-boundary proposal addresses the geometry of time within our universe. It doesn't address the question of why there's a universe at all, or whether there are other universes, or whether the whole framework of space-time is just one layer of a deeper reality. And that's where the next piece of the puzzle comes in. Because even if you accept that the universe has no boundary in time, that doesn't mean it's been around forever. There's a theorem, a mathematical proof, that says, under very general conditions, any universe that's been expanding, even on average, cannot be extended infinitely into the past. It has to have a boundary somewhere. The theorem is called the Bordy-Guth-Vilenkin theorem, and it applies to eternal inflation, to bouncing models, and yes, even to proposals like Hawking's. It doesn't tell you what the boundary is or what's on the other side, but it tells you there is a boundary, a past edge, a point beyond which the classical space-time description breaks down. The no-boundary proposal tries to smooth out that edge, to replace it with a round cap instead of a sharp singularity. But the BGV theorem says you can't avoid having an edge entirely. There has to be a past boundary. The universe, in some form, had to start. And that brings us full circle to the question we've been dancing around this entire time. Did time have a beginning? And if it did, what does that actually mean? The no-boundary proposal says the universe doesn't have a starting edge because time itself curves smoothly into space at the origin. No singularity, no sharp boundary, no first moment. It's elegant, it's bold, and it sidesteps the whole question of what came before by saying before doesn't exist. Time doesn't extend infinitely backward, but it also doesn't have a point where it starts. It's finite but unbounded, like the surface of a sphere. Walk south from the equator and eventually you reach the South Pole. But there's no edge there, no point beyond which you can't go. You just hit the pole and every direction becomes north. Time, in Hawking's picture, works the same way near the Big Bang. You can trace the history backward only so far before the geometry rounds off, and the concept of earlier stops making sense. That's a powerful idea. It removes the need for initial conditions. It eliminates the singularity. It makes the universe self-contained. But it doesn't settle the question of whether the universe had a beginning, not definitively. Because in 2003, 3 physicists published a theorem that said something uncomfortable about universes that expand. The theorem was short, 4 pages in Physical Review letters, straightforward, almost shockingly simple given the implications, and what it said was this: any universe that has been expanding, on average, cannot be extended infinitely into the past. There has to be a boundary, a past edge, a point where the classical description breaks down and you can't keep tracing the history backward. The universe, in some sense, had to start, somewhere, somehow. The theorem was written by Arvind Borde, then a physicist at Long Island University, Alan Guth, the MIT physicist who invented inflation, and Alexander Vilenkin, a cosmologist at Tufts University who has spent decades thinking about quantum cosmology and the origin of the universe. The 3 of them are usually referred to by their initials: Borde, Guth, Vilenkin, BGV, the BGV theorem. It's one of the most cited results in modern cosmology, and also one of the most misunderstood, because what it actually proves is not what most people think it proves. It doesn't say the universe popped into existence out of nothing. It doesn't say time started at a specific moment. It doesn't even say there was a Big Bang in the traditional sense. What it says is that if a space-time has been expanding on average along certain paths, then those paths cannot be extended infinitely into the past. They're incomplete. They have a boundary. What's on the other side of that boundary, the theorem doesn't tell you. It just tells you the boundary has to be there. Let's unpack that. The BGV theorem is about geodesics. A geodesic is the path a particle follows through space-time when no forces are acting on it. It's the straightest possible path in a curved geometry. In flat space, a geodesic is a straight line. In curved spacetime, geodesics bend. Light travels along null geodesics. Massive particles travel along time-like geodesics. The theorem focuses on time-like and null geodesics that are directed backward in time. You start at some point in the present and trace a path backward, following the history of a particle or a light ray as the universe gets smaller and denser. The question the theorem asks is simple: can you keep tracing that path backward forever, or does it eventually hit a boundary? The answer depends on whether the universe is expanding. Not whether it's expanding right now, but whether it's been expanding on average along the geodesic you're tracing. The theorem introduces a quantity called the Hubble parameter, the rate of expansion at any given point along the path. If the average value of the Hubble parameter along a backward-directed geodesic is positive, meaning the universe has been expanding on average, then that geodesic cannot be extended infinitely into the past. It's incomplete. There's a past boundary. The path ends. Or more precisely, it reaches a point where the classical space-time description no longer applies, and you need new physics to go further. That's it. That's the theorem. It's a kinematical result. It doesn't depend on what kind of matter or energy is driving the expansion. It doesn't require assumptions about gravity being attractive or repulsive. It doesn't care about the energy conditions that usually show up in cosmological proofs. It just looks at the expansion history and draws a conclusion about the geometry. If the universe has been getting bigger on average, you can't trace its history back infinitely far using the classical framework. There has to be a boundary. The result is surprisingly robust. It applies to all sorts of cosmological models, standard Big Bang cosmology with or without inflation, eternal inflation, Even some bouncing models, if they include an overall expansion when you average over long timescales. The only way to avoid the theorem is to have a universe that's not expanding on average, a universe that's contracting or static or oscillating in a way that the average expansion rate over the entire history is 0 or negative. But most of the universe we observe is expanding. The galaxies are moving apart. The space between them is stretching. And the theorem says that if that's been happening on average, then the spacetime is geodesically incomplete to the past. Guth has been clear about what this means for eternal inflation, the model he helped develop. Eternal inflation says that once inflation starts in some region, it never completely stops. It keeps going in some parts of the universe, even as other parts exit the inflationary phase and become universes like ours. The process generates an infinite number of bubble universes, each with its own Big Bang. And because the inflating regions grow exponentially, the total volume of space that's still inflating increases over time. Inflation becomes self-sustaining. It runs forever into the future. But the BGV theorem says it can't run forever into the past. Even though eternal inflation is called eternal, it's only eternal going forward. Trace it backward and you hit a boundary. The inflationary phase had to start. It had to come from something. The theorem doesn't tell you what that something is, but it tells you there has to be a something. Vilenkin has said it plainly. A universe that is on average expanding is geodesically incomplete to the past. He's used the theorem to argue that the universe, or at least the inflating part of it, must have had a beginning, not necessarily a singular point like the traditional Big Bang singularity, but a boundary. A place where the classical description ends and you need quantum cosmology or some other framework to describe what comes next. Vilenkin's own work on quantum cosmology involves the idea that the universe tunneled into existence from nothing, a quantum fluctuation that created a tiny patch of inflating space that then grew into the cosmos we observe. The BGV theorem, in his view, supports that picture. If spacetime is past incomplete, then you need something other than classical spacetime to explain the origin. Quantum mechanics is the natural candidate. Guth is more cautious. He's pointed out that the theorem tells you where classical general relativity breaks down, but it doesn't tell you what replaces it. You could have a quantum bounce. You could have a multiverse where our inflating region budded off from some larger structure. You could have something else entirely. The theorem rules out an eternally inflating spacetime that extends infinitely into the past, but it doesn't rule out the possibility that there's a pre-inflationary phase described by different physics. The boundary the theorem identifies is not necessarily a beginning in the absolute sense. It's just the edge of where the classical equations work. This is where the misunderstandings start. The BGV theorem is widely cited in debates about whether the universe had a beginning. Some people treat it as proof that the universe was created, that there was a first moment, that time itself started at some definite point. But that's not what the theorem says. It says space-time, as described by general relativity, is incomplete to the past if the universe has been expanding on average. Incomplete means the equations hit a boundary. They can't be extended further without adding new physics. But a boundary is not the same thing as a beginning. A boundary is a place where your model stops working. What's on the other side of the boundary is an open question. Board, Guth, and Vilenkin were explicit about this in their paper. They wrote, "Our argument shows that inflationary models require physics other than inflation to describe the past boundary of the inflating region of spacetime." They're not claiming to have proven that the universe came from nothing or that time started at a specific moment. They're saying that if your model involves inflation or any other kind of sustained expansion, you can't avoid having a past boundary. And whatever is at that boundary, it's not described by the classical inflationary equations. You need something else: quantum gravity, a different phase of spacetime, a different kind of cosmology, something. The theorem's power comes from its generality. It doesn't depend on specific assumptions about the matter content of the universe or the form of the gravitational field equations. It's a geometric result. If the expansion rate, averaged along a geodesic, is positive, the geodesic is incomplete. That applies to a huge range of models. It's very hard to build a cosmology that avoids the theorem without giving up the idea that the universe has been expanding. And since we observe expansion, that's a tough thing to give up. But there are loopholes. The theorem assumes the average expansion rate is positive. If you have a model where the universe contracts for part of its history and expands for another part, and the contraction is strong enough that the average expansion rate over the whole history is 0 or negative, the theorem doesn't apply. Some cyclic models work this way. The universe expands, then contracts, then bounces and expands again. If the contracting phases are long enough and deep enough, the average expansion rate over a full cycle might not be positive. The BGV theorem wouldn't rule out an infinite sequence of cycles in that case. Vilenkin and others have argued that most realistic cyclic models don't actually avoid the theorem because the contracting phases tend to be short compared to the expanding phases, so the average is still positive. But it's not a closed case. The details matter. Another loophole is quantum gravity. The BGV theorem is a classical result. It uses the equations of general relativity, which treats spacetime as a smooth, continuous structure. But we know that at very small scales, quantum effects take over. Spacetime itself becomes uncertain, fluctuating, possibly discrete. The BGV theorem tells you where the classical description breaks down, but it doesn't tell you what the quantum description looks like. It's entirely possible that the boundary identified by the theorem is not a hard edge, but a fuzzy quantum region where the concept of a geodesic stops making sense. In that case, you can't extend the geodesic further, but not because there's nothing beyond it. Because the framework you're using, classical geodesics, doesn't apply anymore. The universe might continue in some quantum sense, but the theorem doesn't see it because the theorem is classical. Loop quantum cosmology offers an example. In LQC, the universe bounces when the density reaches the Planck scale. The bounce replaces the singularity. And because the universe is contracting before the bounce and expanding after, the average expansion rate over a long enough timescale might be close to 0. More importantly, near the bounce, the geometry is quantum. Geodesics, as defined in classical general relativity, don't exist in that regime. The BGV theorem applies to the expanding phase after the bounce, and it tells you that phase is past incomplete. But the incompleteness doesn't mean the universe didn't exist before. It just means the classical description ends at the bounce, and you need the quantum framework to go further. The theorem points to a boundary. Loop quantum cosmology tells you what's on the other side. Penrose's conformal cyclic cosmology also sidesteps the theorem in a different way. In CCC, the universe doesn't contract and then bounce. It expands forever, but the infinite future of one aeon is conformally equivalent to the Big Bang of the next. The expansion never stops. The average expansion rate is always positive. So the BGV theorem should apply, right? It does. It tells you that each aeon is past incomplete. But Penrose's model stacks the aeons one after another, extending backward infinitely. The classical spacetime within each aeon is incomplete, but the full structure, the infinite chain of aeons, has no beginning. The theorem applies to each individual aeon, but not to the eternal sequence. Whether that's a legitimate way around the theorem is debatable. Vilenkin would probably say it's cheating, that you're just shifting the boundary problem to a different level. Penrose would say the boundary is real within each Aeon, but the larger structure has no boundary. It's an unresolved argument. The no-boundary proposal handles things differently. Hawking's model says the boundary exists, but it's smooth. Time curves into space, and the geodesics that the BGV theorem talks about end not at a sharp edge, but at a rounded cap. The theorem still applies. The space-time is still past incomplete, but the incompleteness is not a singularity. It's a gentle rounding off. And because the boundary is described using imaginary time, a fully quantum framework, the classical notion of a geodesic being incomplete is not a problem. You've already moved beyond the classical picture. The theorem tells you where to stop using classical general relativity. The no-boundary proposal tells you what to use instead. The two ideas are compatible. The theorem points to a boundary. The proposal describes what the boundary looks like. So what does the BGV theorem actually prove? It proves that classical general relativity cannot describe the entire history of an expanding universe. There has to be a past boundary, a place where the equations stop working and you need new physics. That's a significant result. It rules out the idea that you can have an eternal, smoothly expanding universe described entirely by classical cosmology. If the universe is expanding on average, then at some point in the past, something other than the usual expansion was happening. A quantum phase, a contracting phase, a transition, something. But the theorem does not prove there was a first moment. It does not prove time started. It does not prove the universe came from nothing. Those are interpretations, not conclusions of the theorem. The theorem is about geodesic incompleteness, not about absolute beginnings. Vilenkin tends to interpret the result as evidence for a beginning, because he thinks the most natural explanation for a past boundary is a quantum creation event. Guth is more open to the possibility that the boundary connects to some earlier phase. Borde, the third author, kept a lower profile in the public debates and generally avoided making strong metaphysical claims. The theorem's role in cosmic origin debates has been enormous. It's cited by scientists, philosophers, and theologians. Some use it to argue that modern cosmology supports the idea of a creation event. Others use it to argue that we simply don't know what happened before the boundary, and we need better physics to find out. The theorem itself is neutral. It's a mathematical result. It tells you what the equations imply under certain assumptions. How you interpret that result depends on your broader views about the nature of time, the applicability of quantum mechanics to cosmology, and what counts as an explanation for the origin of the universe. One thing the theorem does make clear is that eternal inflation is not as eternal as the name suggests. Guth himself has said this repeatedly. Inflation is eternal to the future but not to the past. Once it gets going, it never completely stops. New inflating regions keep appearing, new bubble universes keep forming, and the process runs forever. But the inflating state itself had to start. The BGV theorem guarantees it. There's a past boundary. What came before that boundary is the question eternal inflation doesn't answer. You need something else. Some models propose that the inflating region emerged from a quantum fluctuation in a pre-existing space-time. Some propose that it tunneled from nothing. Some propose that it budded off from a larger multiverse structure. None of these ideas are proven. They're speculative extensions. But the BGV theorem tells you that you need one of them. You can't avoid the question of what came before the expansion by appealing to eternal inflation. The expansion has a past edge. The surprising thing is how simple the proof is. The paper is only 4 pages long. The math is straightforward. You define a parameter that measures the expansion rate along a geodesic. Show that if the average is positive, the geodesic can't extend infinitely into the past, and you're done. No complicated field equations, no exotic assumptions, just basic geometry. The result follows almost immediately from the definition of expansion, and yet it applies to an enormous range of cosmological models. That's what makes it powerful. It's not a model-specific result. It's a general feature of expanding spacetimes. But general doesn't mean universal. The theorem has assumptions. The main one is that the average expansion rate along the geodesic is positive. If that assumption doesn't hold, the theorem doesn't apply. And there are ways to construct cosmologies where it doesn't hold. Cyclic models where the universe spends as much time contracting as expanding. Models with exotic matter that violates the usual energy conditions. Models where the notion of a geodesic breaks down because spacetime becomes fundamentally discrete or non-commutative. The BGV theorem is robust, but it's not ironclad. It tells you what happens in the classical continuum limit under the assumption of average expansion. Step outside that regime and all bets are off. Vilenkin has argued that most of the proposed loopholes don't work. He's examined cyclic models and found that in realistic scenarios, the entropy buildup over multiple cycles makes them unsustainable. You can't keep bouncing forever because each bounce leaves the universe with higher entropy, and eventually you run out of room. He's looked at quantum cosmology models and argued that even if you replace the classical boundary with a quantum state, you're still left with the question of why that quantum state exists and where it came from. He's concluded, tentatively but firmly, that the universe probably had a beginning in the sense that there's a past boundary beyond which nothing existed. Not necessarily nothing in the sense of empty space, but nothing in the sense of no spacetime, no physical laws, no structure at all. Guth is less willing to go that far. He acknowledges that the BGV theorem rules out an eternally inflating past within the classical framework, but he's open to the possibility that the boundary connects to something else. He's said in interviews that the theorem shows our current models are incomplete, not that the universe is incomplete. The difference matters. An incomplete model is a model that needs to be extended or replaced. An incomplete universe is a universe that has an edge beyond which there's literally nothing. Guth leans toward the first interpretation. Vilenkin leans toward the second. Both are consistent with the theorem. The philosophical implications are stark. If the universe has a past boundary, then either something came before the boundary or nothing did. If something came before, then that something needs its own explanation, and you're back to the same question one level up. If nothing came before, then you're saying the universe emerged from a state of non-existence, which raises the question of how that's possible. Quantum mechanics offers one answer. Quantum fluctuations can create particles out of nothing, borrowing energy from the vacuum for a brief moment before paying it back. Maybe the universe is a quantum fluctuation writ large, a bubble of spacetime that tunneled into existence from a state of no spacetime. The energy balance works out because the positive energy of matter is offset by the negative gravitational potential energy, making the total energy of the universe roughly zero. It's allowed by the equations. Whether it's what actually happened is another question. The BGV theorem doesn't tell you which interpretation is right. It just tells you there's a boundary. What you do with that information depends on your broader framework. If you think the universe is fundamentally quantum, the boundary might be a quantum creation event. If you think the universe is part of a larger multiverse, the boundary might be the edge of our region, not the edge of everything. If you think time itself is emergent, a feature that only makes sense at macroscopic scales. The boundary might be the point where the concept of time breaks down and you need a different way of talking about the structure of reality. All of these are live options. The theorem doesn't pick among them. What the theorem does do is close off one particular escape route. You can't avoid the origin problem by saying the universe has just been expanding forever. Not if you want to use classical general relativity. The equations don't allow it. If the universe has been expanding on average, there's a past boundary. You have to deal with it. You have to explain what's at the boundary, or what's beyond it, or why the boundary doesn't require an explanation. You can't just wave it away and say the universe has always been here in its current form. The BGV theorem says no, there's an edge. Classical space-time ends, something else begins, or nothing begins, but you can't ignore the boundary. This matters because so many cosmological models try to push the origin problem back by invoking eternal processes, eternal inflation, eternal cycling, eternal quantum fluctuations in a timeless void. The BGV theorem says that within the classical framework, those processes can't run eternally into the past. They have a boundary. They started. Whether that boundary is a beginning in the absolute sense is still an open question. But the boundary is there. It's not something you can model away by making the universe older or larger or more complicated. It's a feature of the geometry. Expanding spacetimes are past incomplete. That's what the theorem says. And it says it cleanly, simply, and with very few assumptions. The theorem has also been misused. It's been cited in arguments that modern cosmology proves the universe was created by a supernatural agent. That's a leap the theorem doesn't support. The theorem is about geodesic incompleteness in classical spacetime. It says nothing about whether the boundary implies a cause, let alone a supernatural one. It's a statement about the limits of a physical theory, not a statement about the existence or non-existence of anything beyond those limits. Vilenkin himself, despite arguing for a beginning, has been clear that the theorem doesn't prove God or any particular metaphysical conclusion. It's a tool, a result, not a proof of anything beyond what it explicitly states. The theorem's real value is that it sharpens the question. Instead of asking whether the universe had a beginning in some vague, undefined sense, you can ask whether the spacetime we inhabit is geodesically complete to the past. And the answer, if the universe has been expanding on average, is no. That's progress. It narrows the problem. It tells you where your current model breaks and where you need to look for new physics. It doesn't solve the origin problem, but it clarifies what the origin problem actually is. It's not about finding a moment labeled time equals zero. It's about understanding what happens at the boundary where the classical description ends. What kind of physics applies there? What does it mean for a geodesic to be incomplete? Can you extend the structure beyond the boundary using a quantum framework, or is the boundary truly the end of the line? Those are the questions the BGV theorem leaves you with. And they're good questions. They're scientific questions. Testable, in principle, if we can develop the right tools and observations. The theorem doesn't tell you the universe was created. It tells you the universe, as described by classical general relativity, has a past edge. What you make of that edge is up to you, but you can't pretend it's not there. The mathematics is too clear. The assumptions are too minimal. The conclusion is too robust. Expanding spacetimes are past incomplete. There's a boundary. And on the other side of that boundary is the next chapter of the story. The part we don't fully understand yet. The part that requires new physics, new concepts, maybe a completely new way of thinking about time and existence. The BGV theorem is not the end of the conversation. It's a signpost pointing toward the edge of the map, and beyond that edge is the enduring mystery. We've spent the better part of this journey dismantling a number, 13.8 billion years. That's the figure you'll find in textbooks, on NASA websites, in museum exhibits about the cosmos. It's presented with confidence, refined to within tens of millions of years. A number so precise it feels like certainty, and in one sense it is certain. We know, with extraordinary accuracy, how long the observable universe has been expanding in its current phase. We can trace the history backward from today, through the formation of galaxies and stars, through the moment when atoms first formed and light could travel freely, all the way back to a hot, dense state that existed 13.8 billion years ago. The evidence for that timeline is overwhelming. The cosmic microwave background confirms it. The abundances of light elements confirm it. The redshifts of distant galaxies confirm it. We're not guessing, we're measuring. But that number does not tell you when the universe began. It tells you when this expansion phase started. And those are not the same thing. That distinction, which should be obvious but somehow keeps getting lost in translation, is the thread running through every model we've examined. Eternal inflation says the expansion we observe is one bubble in an infinite process that's been running forever and will keep running forever. The Big Bounce says the expansion is what happened after a prior contraction reached a quantum limit and reversed course. Conformal cyclic cosmology says the expansion is the continuation of a previous aeon's infinite expansion, conformally rescaled into a new beginning. The no-boundary proposal says the expansion emerges from a smooth quantum geometry where the concept of a starting point dissolves into meaninglessness. And the BGV theorem says that whatever model you prefer, if it involves expansion, there's a past boundary where the classical equations break down and you need something else to describe what comes next. None of these ideas agree with each other, not completely. They're built on different foundations, use different mathematics, make different assumptions about what kind of physics applies at the edge of the known. But they all converge on the same basic conclusion: the Big Bang, the moment we've been calling the beginning for nearly a century, is not the origin of everything. It's a transition, a phase change, a boundary between one state and another. What came before that boundary, if before even makes sense, is still an open question. And the answer, when we find it, is going to look nothing like the simple story we've been telling ourselves. The standard narrative goes like this: in the beginning, there was nothing. Then, for reasons we don't understand, the universe exploded into existence. Space, time, matter, energy, all of it appeared in a singular instant. The universe expanded from a point of infinite density, cooled, particles formed, atoms assembled, stars ignited, galaxies gathered, and here we are. It's a creation story. Not religious, but structured the same way. A definite start, a moment when everything began. And for most of the 20th century, that story worked. It explained the observations, it fit the data. It gave us a framework for understanding cosmic history. But the more precisely we measured the universe, the more we refined our models, the more cracks appeared in the foundation. The singularity at the start of the story is not a feature, it's a bug. A sign that the equations have hit their limit, and every attempt to fix the bug has led to the same uncomfortable realization. The universe probably didn't start. It transitioned. Inflation was the first hint. Alan Guth proposed it in 1981 to solve specific problems with the standard Big Bang model. The universe looked too smooth, too flat, too finely tuned. Inflation explained all of that by saying the universe went through a brief phase of exponential expansion right after whatever came before the Big Bang. That expansion stretched space smooth, flattened the geometry, and set the initial conditions for the hot, dense phase we call the Big Bang. Inflation worked so well that it became the default assumption, but it also opened a door. If there was a phase before the Big Bang, what was happening during that phase? Where did the inflating state come from? And once you start asking those questions, the whole idea of a singular beginning starts to look shaky. Eternal inflation pushed the door wider. If inflation happened once, it's probably still happening somewhere. The same quantum fluctuations that ended inflation in our region are also creating new inflating regions elsewhere. The process is self-sustaining. It runs forever into the future. And if it runs forever forward, why wouldn't it run forever backward? The BGV theorem closed that particular loophole. It proved that even eternal inflation has a past boundary. The inflating state had to start. But the boundary the theorem identifies is not a moment of creation. It's the edge of where classical physics works. What's on the other side is a question for quantum cosmology, not classical general relativity. The theorem tells you where your current model breaks. It doesn't tell you there's nothing beyond the break. Loop quantum cosmology offered one answer. If space-time is quantized at the smallest scales, if there's a minimum volume and a maximum density, then the universe never collapses to a singularity. It hits a floor and bounces. The Big Bang is not the beginning. It's the moment when a contracting universe reached the Planck scale and rebounded into expansion. Before the bounce, there was a universe. A different universe, contracting, getting denser, but still a universe with structure and history. The bounce erases most of the details, but not all of them. Some information survives. The pre-bounce universe is not completely inaccessible. It left fingerprints. We just haven't found them yet. Or maybe we have, and we don't recognize them because we don't know what we're looking for. Penrose's conformal cyclic cosmology went a different direction. No contraction, no bounce. Just an infinite chain of cosmic epochs, each one ending in a cold, empty, timeless state that smoothly transitions into the hot, dense start of the next. The far future and the distant past are the same thing, just viewed through different conformal lenses. The universe recycles itself not by collapsing and re-expanding, but by losing track of scale. When nothing has mass and time stops meaning anything, the infinitely large and the infinitely small become indistinguishable. The end of one aeon is the Big Bang of the next. No first epoch, no final epoch. Just an eternal procession of universes, each one unique in detail but identical in structure. Hawking's no-boundary proposal took yet another route. Time itself, near the Big Bang, curves into space. The distinction between past and future dissolves. The universe doesn't have a starting edge any more than the Earth has a southernmost point beyond the South Pole. You can trace the history backward only so far before the geometry rounds off and the concept of earlier stops making sense. The boundary is smooth. It's described in imaginary time, a fully quantum framework. The universe is finite in temporal extent but unbounded. It simply is. No cause, no creation event, no moment when the clock started ticking. Just a self-contained spacetime, with no need for anything outside it to explain its existence. These models are not compatible with each other. You can't mix and match. Eternal inflation and the Big Bounce make different claims about what came before the Big Bang. CCC and the no-boundary proposal use entirely different mathematical structures to describe the origin. They're competing frameworks, not complementary ones, and yet they all share a common thread. They all treat the Big Bang as a boundary, not a beginning. A place where one kind of physics gives way to another. The 13.8 billion year clock measures how long it's been since that boundary, not how long the universe has existed. The universe itself, whatever that word means in the context of these models, might be far older, or it might be eternal, or the question of its age might not even make sense once you step outside the classical framework. The observational evidence hasn't settled the debate. We have the cosmic microwave background, the most detailed map of the early universe ever made. We have measurements of the expansion rate, the density of matter, the distribution of galaxies. We have gravitational wave detectors listening for echoes from the first moments after the Big Bang. We have James Webb looking deeper into cosmic history than any telescope before it. And all of that data is consistent with the standard inflationary Big Bang model. But it's also consistent with several alternatives. The differences between the models are subtle. The signatures they predict are faint. Detecting them requires precision we don't quite have yet, and in some cases, precision we might never have. The universe is only so transparent. Some information is lost forever behind horizons we can't cross. That's frustrating if you want definitive answers, but it's also liberating. The fact that we don't know, the fact that the question of cosmic origins is still open, means there's room for genuine discovery. We're not filling in footnotes, we're mapping uncharted territory. Every new observation, every refinement in the data, every improvement in our theoretical tools brings us closer to understanding what actually happened at the boundary, or whether the boundary is even the right way to think about it. Science doesn't progress by confirming what we already believe. It progresses by finding the places where our beliefs fail and figuring out what replaces them. The shift in perspective is profound. For most of human history, the question of cosmic origins was a question for religion. The universe was created. By whom or by what depended on which tradition you followed, but the structure was the same. A moment of creation, a beginning. Science, when it finally turned its attention to cosmology, adopted the same framework. The Big Bang became the secular creation event, the moment when everything started. But the more we've learned, the less that framework fits. The singularity is not a moment of creation, it's a placeholder for ignorance, a sign that our equations don't work there. And once you accept that, the whole notion of a cosmic beginning starts to look like a category error. We've been asking when the universe started, but maybe the universe doesn't start. Maybe it cycles. Maybe it transitions. Maybe it emerges from a quantum state where time doesn't exist yet. Maybe it's embedded in a larger structure that's always been here in one form or another. All of those possibilities are live options. None of them have been ruled out. The interplay between observation and theory is where the progress happens. Theory proposes a model. Observation tests it. If the model fails, you refine it or replace it. If it survives, you push it harder, look for new predictions, design better experiments. Loop quantum cosmology predicts specific features in the early universe that might show up in the CMB. Eternal inflation predicts a multiverse with varying physical constants, some of which might leave observable imprints. CCC predicts Hawking points and concentric circles. The no-boundary proposal predicts a certain quantum state for the universe that determines probabilities for different large-scale structures. These are testable claims, not easily testable, not always cleanly testable, but testable in principle. That's what separates science from philosophy. You can argue about interpretations all you want, but eventually you have to look at the sky and see if the universe agrees with you. The limits of current physics are real. General relativity breaks down at the singularity. Quantum mechanics doesn't have a framework for describing space-time itself. We don't know how to combine the two. String theory tries. Loop quantum gravity tries. Other approaches try. But none of them are finished. None of them have made predictions that we've been able to test and confirm. We're stuck with partial theories that work beautifully in their respective domains but refuse to talk to each other at the boundary. And the boundary is exactly where the origin question lives. You can't answer what came before the Big Bang without a theory that works at the Planck scale, where quantum effects and gravitational effects are both strong. We don't have that theory yet. We might not have it for decades, maybe longer. But not having the theory doesn't mean we can't make progress. The BGV theorem is a perfect example. It's a rigorous mathematical result that applies to any expanding spacetime, regardless of what kind of matter or energy is driving the expansion. It tells you something concrete. If the universe has been expanding on average, the spacetime is past incomplete. There's a boundary. You can't avoid it by making the universe older or invoking eternal processes. The boundary is there. The theorem doesn't tell you what's at the boundary, but it narrows the problem. It tells you where to look, and that's progress. You've gone from a vague question about whether the universe had a beginning to a specific question about what happens at a geodesic boundary in an expanding spacetime. The second question is harder, but it's also more tractable. It's a question you can attack with math and physics, not just philosophy. The ongoing nature of scientific inquiry is not a weakness, it's the whole point. Science is not a collection of answers, it's a method for asking better questions. The fact that we don't know what came before the Big Bang, the fact that we're still debating whether that question even makes sense, is not a failure of science. It's evidence that science is working. We've reached the edge of what our current theories can explain, and instead of stopping there and declaring the rest unknowable, we're building new theories, designing new experiments, refining our understanding of what the question is actually asking. That process never ends. There will always be another boundary, another place where the equations break, and you need something new. That's not depressing. That's the entire adventure. The profound realization is this: the universe is not a story with a beginning, a middle, and an end. It's a structure, a geometry, a set of fields and particles and interactions governed by laws we're still figuring out. The 13.8 billion year age is a feature of our local patch of that structure, not the age of the structure itself. We live in a bubble, an observable region, and we've traced its history back to a hot, dense state that existed 13.8 billion years ago. But the structure might be far larger. It might be infinite. It might be eternal in some sense we don't fully understand yet. Or it might have started in a way that doesn't involve time in the usual sense, making the question of when it started meaningless. That shift in perspective, from a definitive beginning to an eternal, cyclical, or emergent cosmos, is one of the most profound intellectual leaps humanity has made. For thousands of years, we assumed the universe had to have a first moment, a creation event, a point where it all started. That assumption is so deeply embedded in the way we think about time and causality that challenging it feels almost heretical. But the evidence is pushing us in that direction, not conclusively, not yet, but consistently. Every time we refine the models, every time we push the observations further, the picture gets more complicated. The simple story of a singular beginning keeps fracturing into more nuanced possibilities. A bounce, a transition, a quantum emergence, an eternal cycle. None of these are proven, but all of them are serious contenders, and they all say the same thing. The Big Bang is not the beginning. It's a doorway, and we're still trying to figure out what's on the other side. The universe doesn't owe us a simple answer. It doesn't care if the origin story fits neatly into the categories we're comfortable with. It just is. And our job, the job of science, is to look at it clearly, measure it carefully, and try not to confuse the limits of our knowledge with the limits of reality. The 13.8 billion year age is one of the most precise measurements in all of cosmology. It's also one of the most misunderstood. It's not the age of everything. It's the age of the observable universe's current expansion phase. What came before that, if anything, is still an open question. And that question leads not to simple answers, but to deeper mysteries, stranger possibilities, and a cosmos far more interesting than the one we thought we understood. We stand at the edge of a map. Behind us, the territory is well charted. We know the history of the universe from about a microsecond after the Big Bang to today. We know how stars form, how galaxies evolve, how the large-scale structure of the cosmos came to be. That's an astonishing achievement. 100 years ago, we didn't even know there were other galaxies. Now we can trace the history of the universe backward through nearly 14 billion years. But ahead of us, beyond the boundary the BGV theorem identifies, beyond the point where classical physics breaks down, the map ends. There are theories, models, ideas, some of them elegant, some of them bizarre, all of them speculative. We don't know which one is right. We might not know for decades. But the fact that we're asking, the fact that we've identified the boundary and we're working to understand what lies beyond it, is itself a kind of answer. Not to the question of where the universe came from, but to the question of what it means to do science at the furthest edge of human knowledge. The cosmos is not finished revealing itself. Every answer we find raises new questions. Every boundary we cross exposes another one further out. The age we thought we knew, 13.8 billion years, is just the beginning of the story, not the beginning of the universe, the beginning of our understanding that the universe might not have a beginning at all. That's the enduring mystery. Not that we don't know the answer, but that the deeper we look, the more we realize the question itself might be built on assumptions that don't hold. Time might not have a start, the universe might not have an edge, existence might not require a cause. These are not comfortable ideas. They don't fit neatly into the way we experience reality. But the universe has never cared about our comfort. It just keeps being what it is. Strange, vast, older than we thought, younger than forever, and entirely indifferent to whether we understand it or not. And that, more than any specific theory or model, is the real revelation. The cosmos doesn't end where our knowledge ends. It just keeps going, and so do we. We started with a number, 13.8 billion years, the age of the universe, except it isn't. It's the age of this expansion phase, the time since the last boundary, the clock reading on a process that might not have a first tick. Every model we examined led to the same uncomfortable place. The Big Bang is not the origin, it's a transition point. Eternal inflation says it's one bubble in an endless process. The Big Bounce says it's what happens when contraction reverses. Conformal cyclic cosmology says it's the moment one aeon becomes another. The no-boundary proposal says it's where time curves into space and the concept of starting dissolves. The BGV theorem says it's a boundary where classical physics stops working and something else takes over. None of them agree on the details, but they all agree on this. The singularity is not real. The beginning is not absolute. The edge of the map is not the edge of the territory. For most of history, the question of origins was settled by authority. Religious, philosophical, cultural. Science promised something different. Not settled answers, but better questions. And the question we're left with now is not when did the universe begin. It's whether beginning is even the right concept. whether time has a start or just changes shape, whether the cosmos emerged once or cycles endlessly, or exists in some timeless quantum state where the whole notion of before and after stops passing. We don't know, and that's not a failure. That's the frontier, the place where the equations break and the observations run out, and the only honest answer is we need to look harder, build better tools, ask sharper questions, accept that the universe might be stranger than any story we've told about it so far. 13.8 billion years is not the age of everything. It's how long we've been paying attention. The universe, whatever it is, was here long before that, and it will be here long after. Indifferent, immense, and utterly unbothered by the fact that we still don't know where it came from, or if it came from anywhere at all.